Welcome, fellow dreamer. You have found a place of calm and rest. This evening, we're going to explore the remarkable journey of the periodic table, a story woven with curious minds, unexpected discoveries, and the quiet order hidden within the elements that make up our world. Accompanied by soothing music and abstract imagery, we'll be uncovering little-known wonders and fascinating stories that gently feed your curiosity as you drift toward sleep. If you enjoy these calm adventures with us, don't be shy. Like, subscribe, and leave a comment to help other smart sleepers dream too. And now, take a deep breath, let your body sink into comfort, and allow your mind to rest and your eyes to close as the tale unfolds before you. Long before laboratories existed, before the very word chemistry entered human language, people looked at the world around them and wondered what everything was made of. When you close your eyes tonight and think about this question yourself, you're joining a conversation that began thousands of years ago, when ancient philosophers sat under Mediterranean skies and pondered the same mystery. Imagine yourself in ancient Greece, around 450 years before the Common Era. The world was a place of wonder and speculation, where natural philosophy, the ancient precursor to science, was just beginning to take shape. In the Greek colonies of Sicily, a philosopher named Empedocles walked among olive groves and volcanic slopes, observing nature with careful attention. He watched fire consume wood, water flow and evaporate, earth crumble in his hands, and wind sweep across the landscape. From these observations, Empedocles proposed something revolutionary for his time. Perhaps everything in existence was composed of just 4 fundamental substances. He called them earth, water, air, and fire. This was not merely poetic imagery. Empedocles genuinely believed these 4 elements were the building blocks of all matter. According to his thinking, everything you could touch, taste, or see was some combination of these 4 essentials mixed in different proportions. A tree contained earth and water. A flame was pure fire consuming air. Even human bodies, he suggested, were intricate mixtures of all 4 elements working in harmony. What made Empedocles' idea so compelling was its elegant simplicity. Rather than imagining that every different substance in the world was fundamentally unique, he proposed a unifying theory. Just as countless words could be formed from a limited alphabet, infinite varieties of matter could arise from 4 basic elements combining and recombining in endless ways. 2 cosmic forces, which he called love and strife, mixed and separated these elements, creating the rich diversity of the natural world. The idea took hold with remarkable strength. Decades later, the philosopher Plato embraced this 4-element system, weaving it into his own philosophy. But it was Aristotle, perhaps the most influential thinker of the ancient world, who refined and promoted the theory with such conviction that it would dominate human understanding for nearly 2,000 years. Aristotle, who lived from 384 to 322 before the Common Era, was a systematic thinker who attempted to organize and explain every aspect of the natural world. He taught in Athens, where students gathered at his school, the Lyceum, to learn about everything from ethics to astronomy. When Aristotle considered the question of what things were made of, he adopted Empedocles' 4 elements, but added crucial refinements. Each element, Aristotle proposed, possessed certain fundamental qualities. Earth was cold and dry. Water was cold and wet. Air was hot and wet. Fire was hot and dry. These qualities weren't just descriptive. They explained how elements could transform into one another. Change one quality, and you could theoretically convert one element into another. Heat up water enough, and it would transform into air in the form of steam. Cool air sufficiently, and it would condense back into water. This framework suggested that elements were not unchangeable substances, but rather different expressions of matter in various states. Aristotle went further still. Beyond the 4 terrestrial elements, he proposed a 5th element called aether or quintessence, the substance of the heavens. While everything on Earth was composed of earth, water, air, and fire in constant flux and change, the celestial realm of stars and planets was made of perfect, unchanging aether. This divine fifth element moved in eternal circles, unlike earthly matter which moved in straight lines, falling down or rising up according to its nature. The power of these ideas cannot be overstated. For more than 15 centuries, anyone who wanted to understand the composition of matter began with these 4 or 5 elements. Scholars in ancient Rome accepted them. When knowledge passed to the Islamic world during the medieval period, Arabic scholars studied and commented on Aristotle's elemental theory. When this learning returned to Europe through translations, Christian philosophers integrated the 4 elements into their understanding of creation. It's important to recognize that these ancient thinkers were not simply wrong in a way we should dismiss. They were doing something profoundly human and necessary. They were trying to find patterns and order in a complex world. Without microscopes, without laboratories, without the accumulated knowledge of centuries of experimentation, they used observation and reason to construct a framework for understanding. The 4 elements were the best answer available to minds working with the tools they possessed. Other traditions developed their own elemental systems. In ancient China, philosophers identified 5 fundamental elements: wood, fire, earth, metal, and water. These weren't merely substances, but dynamic forces that interacted in cycles of creation and destruction, deeply influencing Chinese medicine, philosophy, and culture. In ancient India, the classical elements numbered 5 as well: earth, water, fire, air, and space or void. Each tradition was independently grappling with the same fundamental question: what is everything made of? Yet even in the ancient world, not everyone accepted the 4-element theory without question. Some Greek philosophers proposed radically different ideas. Leucippus and his student Democritus, working around the same time as Empedocles, suggested that matter was composed of tiny, indivisible particles they called atoms, from the Greek word atomos, meaning uncuttable. These atoms, they speculated, were infinite in number and eternally in motion, combining and separating to form all the substances we observe. Different types of atoms existed for different materials, and the properties of objects arose from the shapes and arrangements of their atoms. This atomic theory was remarkably prescient, anticipating ideas that would not be properly developed for more than 2,000 years. Yet it remained a minority view in the ancient world, largely because Aristotle's influence was so overwhelming, and because the atomic theory of Democritus lacked the experimental evidence that would later validate it. As the centuries passed and the ancient world gave way to the medieval period, the 4-element theory became not just a scientific framework, but part of the very fabric of how people understood reality. The elements appeared in poetry, in medical theory, in explanations of human personality and temperament. Yet beneath this long stability, seeds of change were slowly germinating. For in the shadowy workshops of medieval alchemists, new substances were being discovered, and new questions were arising. Questions that the ancient framework could not adequately answer. The journey toward truly understanding the elements was just beginning. As the classical world faded and Europe entered the medieval period, a peculiar group of practitioners emerged who would profoundly influence our understanding of matter, though not in the ways they intended. These were the alchemists, and their laboratories were places of mystery, filled with bubbling flasks, glowing furnaces, and the acrid smell of substances being heated, mixed, and transformed. The alchemists inherited the ancient Greek understanding of elements, but they added something new to this framework, an obsessive, almost spiritual quest to transmute base metals into gold. This dream consumed countless individuals across centuries, leading them down winding paths of experimentation that would accidentally lay the groundwork for modern chemistry. Even as they chased an impossible goal, in dimly lit workshops from Alexandria to Prague, alchemists worked with substances that we would recognize today as true elements, though they didn't understand them as such. Sulfur, with its distinctive yellow color and pungent smell when burned, featured prominently in their work. Mercury, that strange silvery liquid metal that flows like water at room temperature, fascinated them endlessly. They observed how mercury could dissolve gold and silver, forming amalgams, and they wondered if this property held the key to transformation itself. The alchemical tradition was shrouded in secrecy. Practitioners wrote in elaborate codes and symbols, partly to protect their supposed discoveries from competitors, and partly because they believed their work was a sacred art that should only be revealed to worthy initiates. They gave poetic names to common substances. Mercury became quicksilver, sulfur was brimstone, and various chemical processes were described using metaphors of death, rebirth, marriage, and spiritual purification. Among the colorful figures of medieval alchemy, we find Jabir ibn Hayyan, an 8th century Arab scholar whose works would influence European chemistry for centuries. Writing in Baghdad during the Islamic Golden Age, Jabir documented careful procedures for distillation, crystallization, and sublimation. He described sulfur and mercury as fundamental principles that combined in different proportions to form all metals. While this theory was incorrect, his methodical approach to laboratory work represented a significant advancement. He treated chemistry as something that required systematic experimentation rather than mere philosophical speculation. In Europe, the 13th century brought figures like Albertus Magnus, a German Dominican friar who wrote extensively about the properties of various minerals and metals. Magnus documented his observations of arsenic, a substance that had been isolated in a relatively pure form by alchemists. Arsenic and its compounds would prove useful in various applications, though the alchemists who worked with it couldn't have understood it as an element in the modern sense. The Renaissance period saw alchemy flourish in new ways. Paracelsus, a Swiss physician born in 1493, challenged the ancient four-element theory and proposed that salt, sulfur, and mercury were the true principles underlying all matter. Though still incorrect by modern standards, Paracelsus pushed alchemy toward practical applications in medicine. He pioneered the use of specific chemicals to treat specific diseases, moving away from the idea that illness resulted from imbalanced humors. His confrontational personality and rejection of traditional medical authorities made him controversial, but his emphasis on observation and experimentation influenced generations of practitioners. The alchemists developed an impressive array of laboratory equipment and techniques that remain relevant today. They perfected the alembic for distillation, created various types of furnaces capable of reaching high temperatures, and learned to work with substances in sealed containers to prevent their escape. They discovered how to produce mineral acids like sulfuric acid, nitric acid, and hydrochloric acid, though they called them by different names. These powerful acids could dissolve metals and other substances in ways that water never could, opening entirely new possibilities for investigation. In their quest to transmute metals, alchemists made observations that in retrospect revealed genuine patterns in how substances behave. They noticed that certain metals resisted corrosion better than others. They observed that some substances melted at low temperatures, while others required intense heat. They documented how different materials combined or refused to combine, and they noted the colors and properties of the products their experiments produced. Without intending to, they isolated several substances we now recognize as elements. Antimony, a brittle silvery metal, was purified by alchemists in the 15th century. Zinc, though used in alloy form for centuries, was recognized as a distinct substance by European alchemists around the 13th century. Phosphorus, discovered accidentally by the German alchemist Hennig Brand in 1669, would become one of the last elemental discoveries made by alchemical methods. Brand's discovery of phosphorus illustrates both the dedication and the misguided theories that characterized alchemy. Convinced that the yellow color of urine might hold the secret to creating gold, Brand collected vast quantities of urine and subjected it to various processes including boiling, heating, and distillation. The result was not gold, but a white, waxy substance that glowed in the dark and burst into flame when exposed to air. This was phosphorus, an element essential to all life and completely unlike anything alchemists had encountered before. Brand attempted to keep his discovery secret, hoping to profit from it, but the method for preparing phosphorus eventually spread throughout the alchemical community. The alchemists operated in a world without clear distinction between chemistry, medicine, metallurgy, and mysticism. They believed that spiritual purity might be necessary for experimental success. They thought the planets and stars influenced chemical reactions. They searched for the mythical philosopher's stone, a substance that could supposedly transmute any metal into gold and grant eternal life. These ideas seem fanciful now, but we must remember that these individuals were working without the conceptual framework that would later make chemistry comprehensible. Despite their incorrect theories, the alchemists made genuine contributions to practical knowledge. They discovered new pigments for artists, developed improved methods for making glass and ceramics, created medicinal preparations that actually worked, and refined techniques for extracting and purifying metals. They accumulated a vast body of observations about how different substances behaved, even if they couldn't properly explain what they were observing. As the 17th century dawned, alchemy stood at a crossroads. The methods had been refined, the equipment had been perfected, and countless observations had been recorded. What was needed now was a new way of thinking about matter itself, a framework that could make sense of all these accumulated facts without invoking spiritual transformation or planetary influences. That revolution in thinking was about to arrive, bringing with it the birth of chemistry as we know it, and a fundamental reassessment of what it meant to be an element. The story of how chemistry emerged from the shadowy world of alchemy required someone willing to question everything that had been accepted for centuries. That person arrived in the form of an Irish natural philosopher with sharp eyes, a sharper mind, and an aristocratic bearing that commanded respect in the scientific circles of 17th century Europe. Robert Boyle was born in 1627 into extraordinary privilege as the 14th child of the Earl of Cork, one of the wealthiest men in the British Isles. His childhood was spent in Lismore Castle in Ireland, surrounded by luxury and learning. From his earliest years, young Robert showed an insatiable curiosity about the natural world, asking questions that went deeper than simple observation. Unlike many sons of nobility who treated education as mere social polish, Boyle approached learning with genuine passion. He traveled to the continent as a teenager, absorbing the new ideas that were beginning to bubble through European intellectual circles, ideas that suggested the universe operated according to mechanical principles that could be understood through careful observation and reason. When Boyle returned to England in his early 20s, he threw himself into experimental work with an energy that would define the rest of his life. He was particularly fascinated by the properties of air, conducting experiments with vacuum pumps that revealed how air had weight and exerted pressure. But his contributions to chemistry would prove even more revolutionary than his work with pneumatics. In 1661, Boyle published a book with a deliberately provocative title, The Sceptical Chemist. The very name announced his intentions. He was positioning himself as someone who doubted, who questioned, who refused to accept the inherited wisdom simply because it had been repeated for generations. The book took direct aim at the foundations of both ancient philosophy and contemporary alchemy. For 2,000 years, the four-element theory of the Greeks had dominated Western thought about matter. Earth, water, air, and fire were considered the fundamental building blocks of everything. Alchemists had modified this slightly, adding their principles of mercury, sulfur, and salt, but the underlying assumption remained the same. All matter was composed of a small number of fundamental substances that could be transmuted from one to another through the right processes. Boyle looked at this system and saw confusion masquerading as knowledge. Through careful experimentation, he demonstrated that the traditional elements could not be extracted from most substances. When you burned wood, for instance, the alchemists claimed you were releasing the element of fire, but Boyle pointed out that this explained nothing. Where did the fire exist in the wood before burning? How could you measure it? How could you predict what would happen in other circumstances? The ancient system, he argued, was built on vague analogies and philosophical assumptions, rather than observable, testable reality. In place of this murky tradition, Boyle proposed something radical and clear. An element, he suggested, should be defined as a substance that cannot be broken down into simpler substances by chemical means. If you could separate something into component parts, it was not an element. Only those substances that resisted all attempts at decomposition deserved to be called elementary. This definition seems obvious to us now, but in Boyle's time it represented a fundamental shift in thinking. He was insisting that chemistry should be based on what could actually be observed and measured in the laboratory, not on what ancient authorities had proclaimed or what fit elegantly into philosophical systems. The question was not whether the four-element theory made logical sense within its own framework, but whether it corresponded to what actually happened when you mixed substances, heated them, dissolved them, and tried to break them apart. Boyle himself did not produce a list of elements according to his new definition. That would come later, through the work of others who would build on his foundation. But he had established the criterion by which substances should be judged. The focus had shifted from philosophical speculation to practical experimentation. Chemistry was beginning its long journey from an art shrouded in symbolism to a science built on evidence. What made Boyle's approach even more powerful was his insistence on precise methodology. He kept detailed records of his experiments, noting weights, temperatures, and conditions. He repeated his experiments to ensure that results were consistent. He invited other natural philosophers to witness his work and verify his findings. This might sound mundane, but it represented a revolution in how knowledge was generated and validated. The solitary alchemist working in secrecy with his cryptic manuscripts was being replaced by the community of scientists, sharing information openly and subjecting claims to rigorous testing. Boyle's personal character reinforced his scientific credibility. He was deeply religious, seeing his investigations of nature as a way of understanding the divine creation. He lived modestly despite his wealth, dedicating his resources to scientific equipment and scholarly pursuits rather than lavish display. He never married, apparently considering such commitments a distraction from his studies. His contemporaries respected both his intellect and his integrity, which helped his revolutionary ideas gain acceptance even among those who might have resisted such challenges to tradition. The impact of the skeptical chemist rippled through the scientific community, slowly but inexorably. Boyle had not overthrown the old system overnight. Many chemists continued to work within alchemical frameworks for decades after the book appeared. But Boyle had planted a seed that would grow into modern chemistry. He had asked the right question: what actually is an element? And he had provided an answer based not on ancient authority, but on experimental reality. As the decades passed and more natural philosophers embraced Boyle's approach, the search began in earnest for substances that met his definition. Scientists started looking at common materials with fresh eyes, asking which ones could be broken down and which ones resisted decomposition. This investigation would lead to one of the most productive periods in the history of chemistry, as element after element was isolated and identified. The invisible components of the very air we breathe would be among the first to reveal themselves to these determined investigators, each discovery building on Boyle's foundational insight that nature should be questioned directly rather than through the lens of inherited assumption. With Robert Boyle's new definition of elements firmly established in the scientific mind, chemists of the 18th century turned their attention to the very air around them. For thousands of years, air had been considered a single simple element, but now, armed with better equipment and Boyle's experimental approach, a new generation of curious minds began to suspect that what we breathe might be far more complex than anyone had imagined. The air itself seemed invisible, intangible, impossible to capture or examine. Yet these pioneering chemists developed clever methods to trap gases, transfer them between containers, and study their properties. They built glass vessels and pneumatic troughs, devices that allowed them to collect gases over water or mercury. With these simple but ingenious tools, they began to separate the atmosphere into its component parts, discovering that air was not one element at all, but a mixture of several distinct gaseous substances. One of the most colorful figures in this gaseous revolution was Joseph Priestley, an English minister and natural philosopher who conducted experiments in his spare time. Priestley possessed an insatiable curiosity and a talent for invention, designing much of his own equipment with remarkable ingenuity. Working in the 1770s, he isolated and studied numerous gases, though he often misunderstood what he had discovered due to the prevailing scientific theories of his time. Priestley's most famous discovery came on August 1, 1774, when he focused sunlight through a magnifying glass onto a sample of mercuric oxide, a reddish powder. The intense heat caused the compound to break down, releasing a gas that Priestley collected in a glass container. When he tested this mysterious gas, he found something extraordinary. A candle burned in it with remarkable brilliance. A glowing ember burst into vigorous flame. Even more astonishingly, when Priestley breathed the gas himself, he reported feeling light and easy, describing the sensation as distinctly pleasant. What Priestley had discovered was oxygen. Though he did not call it that, he named it dephlogisticated air, believing it to be air that had been purified by having phlogiston removed. Phlogiston theory, the dominant chemical doctrine of the time, held that a fire-like element called phlogiston escaped from materials when they burned. Priestley's entire interpretation was backwards, yet his experimental observation was impeccable. He had isolated one of the most important elements for life on Earth. Around the same time, a wealthy and peculiarly shy English scientist named Henry Cavendish was conducting his own investigations into gases. Cavendish was an eccentric figure who avoided social contact whenever possible, communicating with his servants through written notes and becoming flustered if women spoke to him at gatherings. Despite his awkwardness in human society, he possessed an extraordinary talent for precise scientific measurement. In 1766, Cavendish isolated a gas he called inflammable air by adding acids to metals, particularly iron and zinc. This gas was remarkably light, lighter than any substance previously known. When ignited, it burned with an almost invisible flame, producing nothing but water. Cavendish had discovered hydrogen, the lightest and most abundant element in the universe. Though like Priestley, he interpreted his findings through the lens of phlogiston theory. He believed he had isolated pure phlogiston itself, not recognizing that he had found an entirely new element. The curious property of hydrogen forming water when burned puzzled scientists for years. How could an inflammable substance combine with another gas to produce something that extinguishes flames? The answer would help overturn centuries of misunderstanding about the nature of elements and compounds, though that revolution would wait for Lavoisier in the next phase of chemistry's development. A third important gas emerged from the work of Daniel Rutherford, a Scottish chemist working in 1772. Rutherford was investigating what remained of air after combustion, and respiration had occurred in a closed container. He carefully removed the carbon dioxide produced and found that a gas remained that would not support combustion or sustain life. Animals placed in this gas quickly suffocated. Candles extinguished in it immediately. Yet this gas made up the majority of ordinary air. Rutherford had isolated nitrogen, though he called it noxious air or mephitic air, believing it to be air saturated with phlogiston. This element comprises nearly 78% of the atmosphere we breathe, yet it had gone unrecognized throughout all of human history until this methodical investigation revealed its presence. Nitrogen is relatively unreactive compared to oxygen, which is why it serves as a diluting medium in the air, preventing the rapid oxidation that would occur if we breathed pure oxygen constantly. These discoveries were interconnected in ways their discoverers didn't fully appreciate. Priestley and Rutherford were friends and correspondents, sharing their findings and discussing their interpretations. Cavendish worked more independently, but was aware of their experiments. All three men were hampered by their commitment to phlogiston theory, which prevented them from understanding the true nature of what they had found. They had the right observations, but the wrong explanations. Other researchers contributed pieces to this gaseous puzzle. Carl Wilhelm Scheele, a Swedish pharmacist working in relative isolation, actually discovered oxygen independently around the same time as Priestley, though his findings were published slightly later. Scheele called it fire-air and recognized its importance for combustion and respiration. He also isolated chlorine and identified numerous other substances, though his modest circumstances and early death prevented him from receiving the recognition his meticulous work deserved. As the 18th century progressed, the list of known gases expanded. Scientists identified carbon dioxide, which Joseph Black had studied earlier in the century, calling it fixed air because it could be absorbed by alkaline substances. They explored the properties of nitrous oxide, hydrogen sulfide, and other gaseous compounds. Each discovery revealed new complexity in the atmospheric mixture that surrounded them. These gaseous elements presented unique challenges for classification. Unlike solid metals or crystalline minerals, gases seemed almost immaterial, difficult to weigh or measure. Yet they clearly had distinct properties and participated in chemical reactions, just as solid substances did. The realization that invisible, weightless-seeming substances could be true elements expanded the concept of what an element could be, preparing the ground for even broader understanding in the decades to come. The work of these 18th century gas chemists demonstrated that careful observation and clever experimentation could reveal hidden complexity in the most familiar substances. The air itself, so commonplace that people had barely thought to question its nature, contained multiple distinct elements, each with unique properties essential for life and combustion. Though these pioneers often misinterpreted their discoveries, their experimental achievements were building blocks for the revolution in chemical understanding that was about to transform science forever. By the late 18th century, chemistry stood at a crossroads. Scientists had isolated numerous gases and substances, but the field remained cluttered with confusing terminology and competing theories about what elements truly were. Into this chaotic landscape stepped a wealthy French tax collector with an extraordinary passion for precision and an elegant laboratory where some of the most careful experiments in scientific history would take place. Antoine Laurent de Lavoisier was born in Paris in 1743 to a prosperous family, and his path seemed destined for law rather than science. Yet even as a young man, he found himself captivated by the mysteries of chemistry and geology. After inheriting considerable wealth, he purchased a position as a tax collector, a job that was both lucrative and deeply unpopular with ordinary citizens. The income from this position allowed him to pursue his true passion, and he transformed part of his Paris home into a magnificent laboratory filled with beautifully crafted instruments of his own design. Lavoisier approached chemistry with the eye of an accountant, insisting that everything must balance. He believed that matter could neither be created nor destroyed in chemical reactions, only transformed. This may seem obvious to us now, but in the 1770s, it represented a radical way of thinking. Previous chemists had rarely bothered to weigh their substances carefully before and after experiments. Lavoisier made precise measurement the foundation of his work. His wife, Marie-Anne Pierrette-Pulse, became his closest collaborator. 13 years younger than her husband, she had married Lavoisier at age 14 to escape an unwanted arranged marriage to a much older man. Rather than remaining merely a society wife, she learned English to translate scientific papers for her husband, mastered the art of detailed scientific illustration to document his experiments, and assisted in the laboratory work itself. The drawings she created of Lavoisier's apparatus remain remarkably clear and beautiful even today. Together, the Lavoisiers conducted painstaking experiments on combustion, the process of burning. At the time, most chemists believed in something called phlogiston, an invisible substance supposedly released when things burned. This theory had dominated chemistry for a century, but it created endless contradictions. Some substances gained weight when they burned, others lost weight. Phlogiston theorists tied themselves in logical knots trying to explain these discrepancies, even suggesting that phlogiston might have negative weight. Lavoisier suspected the truth was simpler and more elegant. Working with the oxygen that Joseph Priestley had recently isolated, Lavoisier showed that burning was not about releasing something, but about combining with something. When substances burned, they combined with oxygen from the air. When metals formed what we call oxides, they were actually joining with oxygen, which explained why they became heavier. The supposed phlogiston did not exist at all. These experiments required extraordinary patience. Lavoisier would heat substances in sealed containers, carefully weighing everything before and after. He showed that the total weight never changed, that matter was simply rearranging itself. Combustion was not a mysterious transformation, but a chemical reaction that could be understood and predicted. In 1789, the same year the French Revolution began its turbulent course, Lavoisier published his masterwork, Traité élémentaire de chimie, or Elementary Treatise of Chemistry. Within its pages appeared something revolutionary, a list of substances he considered to be true elements, substances that could not be broken down into simpler components through any chemical means known at the time. His list contained 33 substances, and while not all of them were actually elements by our modern understanding, it represented the first serious attempt to catalogue the building blocks of matter. He included oxygen, nitrogen, and hydrogen among the gases. He listed carbon, sulfur, and phosphorus. He included many metals like gold, silver, iron, copper, and zinc. Some substances on his list, like lime and magnesia, would later be shown to be compounds rather than elements, but Lavoisier could only work with the knowledge and techniques available to him. Just as importantly, Lavoisier reformed chemical naming, replacing the colorful but confusing names inherited from alchemy with systematic terminology based on composition. No longer would chemists speak of oil of vitriol or butter of antimony. Instead, compounds would receive names that revealed their component elements. This new language made chemistry clearer and more accessible to anyone willing to learn its principles. Lavoisier's approach transformed chemistry from an art filled with mysterious transformations into a science based on measurement and reason. He demonstrated that careful experimentation could answer ancient questions about the nature of matter. His law of conservation of mass became a cornerstone of chemical thinking, and his list of elements provided a foundation that others would build upon. Yet even as his scientific reputation soared, his work as a tax collector placed him in growing danger. The French Revolution, which had begun with such hope for reform, descended into terror and paranoia. In 1793, the revolutionary government arrested Lavoisier along with other tax collectors, accusing them of crimes against the people. His scientific achievements meant nothing to the revolutionary tribunal. Marianne fought desperately to save her husband, but the revolutionaries were unmoved by pleas or reason. On May 8, 1794, Antoine Lavoisier was executed by guillotine at the age of 50. The mathematician Joseph Louis Lagrange reportedly said, "It took them only an instant to cut off that head, but France may not produce another like it in a century." His wife survived the terror and eventually recovered many of his papers and instruments. She never remarried, dedicating herself to preserving her husband's scientific legacy. The elegant laboratory where they had worked together stood silent, but the principles Lavoisier had established lived on, forming the bedrock upon which the next generation of chemists would build an even deeper understanding of elements and their properties. As the 18th century drew to a close, chemistry possessed a new rigor, a new language, and a growing list of elements waiting to be organized into patterns not yet imagined. The dawn of the 19th century brought with it a remarkable invention that would transform chemistry forever. In Italy, Alessandro Volta had been experimenting with different metals and chemical solutions, driven by a fascinating controversy about whether electricity came from living tissue or from the metals themselves. His curiosity led him to stack alternating discs of zinc and copper, separated by cloth soaked in salt water, creating what he called an electric pile. When he connected wires to the top and bottom of this tower of metals, a steady electric current flowed. The battery had been born. News of Volta's invention spread across Europe like wildfire, reaching the scientific societies and research laboratories where natural philosophers gathered to discuss the latest discoveries. One of the most enthusiastic recipients of this news was a young man in England named Humphrey Davy, whose passion for chemistry was matched only by his skill at public demonstration and his remarkable gift for experimentation. Davy was an unusual figure in the scientific establishment. Born in Cornwall to a family of modest means, he had apprenticed to a surgeon before discovering his love for chemistry. He possessed a poet's sensibility alongside his scientific mind, counting Samuel Taylor Coleridge among his friends. But it was his fearless approach to experimentation that would make him famous. He had already gained notoriety for inhaling various gases to observe their effects, including the euphoric properties of nitrous oxide, which became known as laughing gas. When Davy learned about Volta's electric pile, his mind immediately leaped to its chemical possibilities. At the Royal Institution in London, where he had become a celebrated lecturer, drawing enormous crowds with his dramatic demonstrations, Davy began constructing ever more powerful batteries. He wondered what would happen if he passed electric current through various chemical compounds. Perhaps electricity, that mysterious force, could break apart substances that had resisted all other attempts at separation. In the autumn of 1807, Davy directed his attention to potash, a common substance that Lavoisier had listed as a compound in his table of elements. Chemists suspected it might contain an undiscovered element, but no amount of heating or mixing with other chemicals had succeeded in breaking it apart. Davy placed a sample of slightly moist potash on a platinum plate connected to one end of his powerful battery, then touched a platinum wire from the other end to the sample's surface. What happened next astonished him. Small globules of a silvery metal appeared at the point where the wire touched the potash. These tiny spheres skittered about on the surface, some bursting into flame with a beautiful violet light. Davy had isolated a new element, one that had never before existed in pure form anywhere on Earth. He named it potassium, after the potash from which it came. The metal was extraordinary. Lighter than water, it was soft enough to cut with a knife, revealing a bright silvery surface that tarnished almost immediately in air. It reacted violently with water, racing across the surface as it decomposed the liquid, releasing hydrogen gas that often ignited. Here was an element with a personality entirely unlike the metals humans had known for millennia. Where gold and copper and iron were stable and solid, potassium was wildly reactive, desperate to combine with other substances. Days later, Davy achieved similar success with soda, another alkaline substance. Through electrolysis, he isolated sodium, which behaved much like its cousin potassium, but was slightly less reactive. The soft silvery metal could be cut like wax and had to be stored under oil to prevent it from reacting with moisture in the air. When thrown into water, sodium would dart about frantically, fizzing and melting into a silvery ball as it decomposed the water. Davy's technique of using electricity to decompose compounds, which he called electrolysis, had proven spectacularly successful. The battery had become a key that could unlock chemical combinations that had resisted all previous attempts at separation. Through electrolysis, he was literally pulling elements apart using the force of electricity. Encouraged by these triumphs, Davy turned his battery toward other alkaline earth substances. From magnesia, he isolated magnesium, a metal that burned with a brilliant white light when heated. From lime, he obtained calcium, another reactive metal that had been hiding in one of the most common substances on Earth. From strontia and baryta, he extracted strontium and barium, adding to his growing collection of metallic elements. These discoveries came in rapid succession during 1807 and 1808. Within just 2 years, Davy had added 6 new elements to chemistry's growing inventory. Each discovery required enormous batteries and careful technique, and each revealed metals with properties that challenged chemists' understanding of how elements could behave. What made these discoveries particularly significant was that they demonstrated electricity's power as a tool for chemical analysis. Before the voltaic pile, chemists had relied on heat and chemical reactions to break compounds apart. But some substances, particularly these alkaline compounds, formed bonds so strong that heat alone could not separate them. Electricity provided a new kind of force, one that could overcome even the strongest chemical attractions. Davy's electrolytic decompositions also revealed something profound about the nature of chemical compounds. The fact that passing electricity through these substances caused them to separate into components suggested that chemical bonds themselves might be electrical in nature. Perhaps, Davy speculated, elements combined because of attractions between positive and negative electrical charges. Though this idea would take many more decades to fully develop, Davy's work with the battery pointed chemistry toward a future where electricity and matter were understood as intimately connected. The elements Davy discovered were reactive metals that existed in nature only in combination with other elements. Sodium and potassium formed the alkali family, metals that reacted vigorously with water and air. Calcium, magnesium, strontium, and barium comprised the alkaline earth metals, slightly less reactive, but still eager to form compounds. These families of similar elements represented some of the first hints that elements might be organized into groups with related properties, though it would take many more years before anyone recognized the full pattern. As news of Davy's discoveries spread through the scientific world, the voltaic pile became an essential tool in chemistry laboratories across Europe. The list of known elements was growing rapidly, and electricity had proven to be the key to unlocking some of nature's most closely guarded secrets. The stage was set for chemistry to transform from a science of careful observation into one of precise measurement and systematic organization. As the 19th century opened, chemistry found itself in a curious position. Thanks to the electrical experiments of Volta and Davy, the list of known elements had grown considerably. Scientists could now isolate pure metals that had previously been locked away in compounds. They could weigh these elements and study their properties. Yet, despite all this progress, a fundamental question remained unanswered. What exactly was an element made of? Why did sodium always behave like sodium? Why did oxygen always combine with other substances in predictable ways? Into this landscape of questions stepped a quiet Quaker schoolteacher from Manchester, England. John Dalton was not a flamboyant experimenter like Humphrey Davy, nor was he connected to the prestigious scientific institutions of London. He spent his days teaching mathematics and natural philosophy to students in the industrial north of England, a region where coal smoke darkened the skies and factories hummed with the new machinery of the Industrial Revolution. Yet it was this unassuming teacher who would propose an idea so powerful that it would transform chemistry from a collection of observations into a true science with predictive power. Dalton had been fascinated by the weather since childhood. Growing up in the Lake District, he kept meticulous records of temperature, rainfall, and atmospheric pressure. This interest in the atmosphere naturally led him to wonder about the nature of gases. Why did different gases behave differently? Why did water vapor rise while other gases settled? These questions occupied his mind during long walks through Manchester's streets and in the quiet hours of evening after his students had gone home. By 1803, Dalton had developed a revolutionary idea. What if, he wondered, each element consisted of tiny, indivisible particles? The ancient Greeks had called such particles atoms, from the word meaning uncuttable. But Dalton's vision went far beyond ancient philosophy. He proposed that all atoms of a given element were identical to each other, with the same weight and the same properties. The atoms of one element, however, differed from the atoms of every other element, particularly in their weight. This was a profound insight. It meant that the fundamental difference between hydrogen and oxygen, between iron and gold, came down to the atoms themselves. Each element had its own unique type of atom, and these atoms were unchangeable and indestructible. When elements combined to form compounds, Dalton suggested, their atoms joined together in simple numerical ratios. Water, for instance, might consist of one atom of hydrogen joined to one atom of oxygen, or perhaps two atoms of hydrogen to one of oxygen. Dalton began assigning relative weights to these atoms. He couldn't weigh an individual atom, of course. Such particles were far too small for any balance, but he could determine how much of one element combined with a given amount of another. He designated hydrogen, the lightest element he knew, as having an atomic weight of 1. Then he compared how much of other elements combined with hydrogen, or with each other, working out a relative scale. His calculations were painstaking. In his dim laboratory, lit by candles and the faint light filtering through Manchester's perpetually overcast skies, Dalton measured and remeasured the proportions in which elements combined. Oxygen, he determined, was about 7 times heavier than hydrogen. Carbon was nearly 5 times heavier. Nitrogen was about 5 times heavier as well. He compiled these measurements into tables, creating the first systematic attempt to assign relative weights to the atoms of different elements. The atomic theory explained so much that had previously seemed mysterious. It accounted for why elements always combined in fixed proportions. When hydrogen and oxygen formed water, they always did so in the same ratio by weight, because the underlying atoms were always combining in the same numerical ratio. If you had 1,000 atoms of oxygen, you needed exactly 2,000 atoms of hydrogen to make water, because each water particle required 2 hydrogen atoms for every oxygen atom. Dalton's theory also explained why you couldn't make half a chemical compound. You couldn't have half an atom, so chemical combinations happened in discrete steps. This was profoundly different from the way people thought about mixing substances. If you mixed water and wine, you could use any proportion you liked, but chemical combinations were different. They followed rules because they were governed by the combination of indivisible particles. In 1808, Dalton published his ideas in a new system of chemical philosophy. The book included careful diagrams showing how he envisioned atoms combining. He drew different elements as circles with different symbols inside them: a dot for hydrogen, a solid circle for oxygen, a circle with a cross for carbon. These simple drawings represented something unprecedented, a visual model of the invisible world of atoms. Not all of Dalton's specific conclusions were correct. He thought water consisted of one hydrogen atom joined to one oxygen atom, when it actually contains two hydrogen atoms for each oxygen. His atomic weights, though groundbreaking, were often inaccurate because of these mistaken assumptions about how atoms combined. Yet the fundamental insight was sound and world-changing. Some chemists embraced Dalton's atomic theory immediately. Others remained skeptical. After all, no one had ever seen an atom, and no one could prove they existed. Perhaps there was some other explanation for why elements combined in fixed proportions. Yet as the years passed, the atomic theory proved increasingly useful. It allowed chemists to predict how much of one substance would be needed to react completely with another. It provided a framework for understanding the growing catalogue of known elements. Dalton himself remained in Manchester, continuing to teach and to refine his theories. He never sought fame or moved to London's Royal Society, though honours eventually came to him. He was more comfortable in his northern city, with his weather observations and his careful experiments. Yet his influence spread across Europe and beyond as chemists began to think in terms of atoms and atomic weights. The atomic theory gave each element a new identity. It was no longer enough to know that gold was yellow and heavy, or that oxygen supported combustion. Now each element had a fundamental property: its atomic weight. This created a new way of comparing elements to each other, a numerical scale that would prove essential in the decades to come. Scientists now had a common language for discussing elements, and more importantly, they had a foundation for discovering the deeper patterns that connected one element to another. As Dalton worked through his later years, gradually going blind, but never losing his curiosity about the natural world, he couldn't have known how his atomic weights would become the crucial clue that would eventually unlock the periodic table's secrets. But he had given chemistry its most fundamental tool, and the elements would never look quite the same again. By the 1820s and into the middle decades of the 19th century, chemists found themselves in a peculiar position. The work of John Dalton had given them a framework for understanding that each element consisted of atoms with specific weights. Humphrey Davy and others had used electricity to unlock new elements from compounds that had resisted all previous attempts at separation. Jöns Jacob Berzelius in Sweden had painstakingly measured and refined the atomic weights of dozens of elements with remarkable precision. The list of known elements was growing longer each year, and with each addition, the periodic puzzle became both more fascinating and more frustrating. Imagine being a chemist in this era, looking at a list of perhaps 50 or 60 elements. You would see some obvious groupings based on behavior. Sodium and potassium clearly belonged together in their violent reactions with water. Chlorine, bromine, and iodine formed another natural family with their similar chemical personalities. Iron, cobalt, and nickel clustered together as metals with magnetic properties. But was there some deeper pattern connecting everything? Was there a hidden order waiting to be discovered, or were the elements simply a random collection of nature's building blocks? The first person to propose a systematic pattern was a German chemist named Johann Wolfgang Dubereiner. Working at the University of Jena in the 1820s, Dubereiner noticed something curious about groups of three elements with similar properties. When he arranged these triads in order of atomic weight, the weight of the middle element was very close to the average of the other two. It was an elegant mathematical relationship, hiding within the chemistry. Consider one of his most striking examples, the triad of chlorine, bromine, and iodine. These three elements were unmistakably related in their chemical behavior, all forming similar compounds, and displaying comparable reactivity. Chlorine had an atomic weight of approximately 35.5, while iodine weighed in at around 127. The middle member, bromine, had an atomic weight of about 80, which was almost exactly the average of the two extremes. The same pattern appeared with calcium, strontium, and barium, and again with sulfur, selenium, and tellurium. Dobereiner published his Law of Triads in 1829, and for a time, chemists found it an intriguing curiosity. Here was evidence that elements weren't arranged randomly, that nature had built them according to some mathematical principle. But the law had obvious limitations. Many elements didn't fit neatly into triads. What about the elements that seemed to stand alone? And why should nature favor groups of three? The law of triads was like catching a glimpse of a larger picture through a narrow window, seeing enough to know something was there, but not enough to understand what it truly was. As more elements were discovered and atomic weights became more accurate, other chemists began their own attempts at organization. In 1862, a French geologist named Alexandre-Émile Beguier de Chamcourtois created what he called the telluric screw. He arranged the elements in order of increasing atomic weight along a spiral drawn on a cylinder. When he wound the spiral so that one complete turn corresponded to an atomic weight increase of 16 units, elements with similar properties lined up vertically along the cylinder's surface. It was an ingenious three-dimensional approach to organizing the elements. De Chamcourtois presented his work to the French Academy of Sciences, but his timing was unfortunate. His paper was published without the crucial diagram that showed the spiral arrangement, making his ideas nearly impossible for other chemists to understand. Additionally, he was a geologist rather than a chemist, which may have caused some to overlook his contribution. His spiral arrangement faded into obscurity, even though it contained genuine insights about periodic relationships. Around the same time, other scientists were drawing closer to the pattern. In Germany, chemist Leopold Gmelin published a table in 1843 that arranged elements into groups sharing similar properties. He organized 55 elements into what he called equivalent series, though he didn't propose any underlying law to explain why these groupings existed. His table was a useful reference tool, but it remained descriptive rather than predictive. The story of these early pattern seekers reveals something profound about how scientific understanding develops. Progress rarely follows a straight line from ignorance to knowledge. Instead, it meanders through partial insights and near misses, with different minds catching glimpses of truth from different angles. Dobereiner saw the mathematical relationships within small groups. De Chamcourtois glimpsed the periodic repetition that occurred as atomic weights increased. Gmelin documented the family resemblances that any careful observer could see. Each contribution added another piece to a puzzle whose complete picture remained frustratingly out of reach. What these early pioneers lacked was sufficient data and a complete understanding of atomic weights. Some elements had been assigned incorrect weights through experimental error. Other elements remained undiscovered, leaving gaps in the pattern that made the full picture impossible to see. And perhaps most importantly, the concepts needed to explain why patterns existed, the ideas about atomic structure and electron arrangement, still lay decades in the future. Yet the search continued, driven by the very human desire to find order in apparent chaos. Chemists of the mid-19th century could sense that they were working with pieces of a grand design. The elements weren't random. They repeated their properties in ways that suggested deep connections. Somewhere in the accumulating data, a great organizing principle was waiting to be discovered. The fragments of understanding were beginning to assemble themselves, though the complete picture would require a different kind of mind, someone willing to make bold leaps and trust in patterns even when the evidence seemed incomplete. The stage was being set for a breakthrough, for someone to look at the same elements that everyone else was studying and see them arranged in a fundamentally new way. The patterns were beginning to emerge from the fog of data, faint but unmistakable, like the first hints of dawn before sunrise. By the mid-1860s, the number of known elements had grown to 63, and the challenge of organizing them had become increasingly urgent. Chemists across Europe wrestled with the question of whether these elements were simply random substances or whether some underlying order connected them. The patterns that Johann Dobereiner and others had glimpsed suggested that nature followed rules, but what those rules might be remained tantalizingly unclear. Into this uncertain landscape stepped an English chemist named John Alexander Rena Newlands. Born in London in 1837, Newlands was a practical man who worked as an analytical chemist, spending his days testing sugar in refineries. He was not a prestigious academic at a grand university, but rather someone who pursued chemistry with a genuine curiosity about the fundamental nature of matter. His background was somewhat unconventional for a scientist of his time. His mother was Italian, and in his youth, Newlands had even traveled to Italy to fight alongside Garibaldi in the struggle for Italian unification. This adventurous spirit would later manifest in his willingness to propose ideas that others found strange. Newlands had been thinking carefully about the elements and their atomic weights, as determined by chemists following in Dalton's footsteps. In 1863, he began publishing his observations about patterns in the elements. What he noticed was striking. If he arranged the elements in order of increasing atomic weight, their properties seemed to repeat at regular intervals. Specifically, he observed that the eighth element often resembled the first, the ninth resembled the second, and so on. This observation reminded Newlands of something entirely outside chemistry, the musical scale. In music, the eighth note of a scale shares fundamental qualities with the first note, just an octave higher. Musicians had understood this pattern for centuries, and it seemed to Newlands that elements might follow a similar law of repetition. In 1865, he formally proposed what he called the law of octaves. Newlands arranged the elements in a table with 7 elements per row, so that similar elements fell into the same columns, starting with hydrogen as the first element, and continuing through calcium. He showed that lithium, sodium, and potassium, all soft, reactive metals, aligned in the same column when arranged by his octave system. Similarly, the elements chlorine, bromine, and iodine, all pungent reactive non-metals, formed another column. The pattern seemed elegant and natural to Newlands. He was excited by his discovery and believed he had uncovered a fundamental law of nature. In August 1865, he presented his law of octaves to the Chemical Society in London, expecting his fellow chemists to share his enthusiasm. The reception was not what he had hoped for. The members of the Chemical Society listened politely, but many were deeply skeptical. To some of the more traditional chemists, comparing elements to musical notes seemed fanciful, even absurd. Chemistry was supposed to be about careful measurement and empirical observation, not analogies to art and music. One member of the society asked, somewhat mockingly, whether Newlands had ever considered arranging the elements in alphabetical order to see if any patterns emerged there as well. This sarcastic comment stung, and it reflected the broader dismissiveness with which Newlands's work was received. The Chemical Society refused to publish his paper in their journal. They saw his octaves as numerology rather than science, a superficial pattern that couldn't possibly represent genuine natural law. After all, the law of octaves worked reasonably well for the lighter elements, but it seemed to break down as Newlands moved to heavier ones. Some elements had to be forced into positions where they didn't quite fit. In several cases, Newlands had placed 2 elements in a single position to make his octave system work, which struck critics as arbitrary manipulation rather than genuine discovery. The scientific establishment's rejection was crushing for Newlands. He had devoted considerable time and thought to his system, and he genuinely believed he had discovered something important about nature. Yet instead of recognition, he faced ridicule. His law of octaves became something of a joke among his peers, an example of what happened when someone let imagination run too far ahead of evidence. For years, Newlands's work languished in obscurity. He returned to his work as an analytical chemist, continuing to refine sugar and conduct practical analyses. The grand questions about the organization of elements seemed to have passed him by, dismissed and forgotten by the scientific community. Yet Newlands had been onto something real. His fundamental insight that the properties of elements repeat periodically when arranged by atomic weight was correct. The problem was not with his basic observation, but with the details of his system. Elements didn't actually repeat every 8th position with perfect regularity. The true pattern was more complex. with some repetitions occurring after 8 elements, others after 18, and still others after 32. The universe's underlying order was more intricate than a simple musical octave. What Newlands lacked was the boldness to break his own rules. When elements didn't fit neatly into his octave system, he forced them into place, rather than questioning whether his specific interval of 8 might be too rigid. He couldn't see that the periodicity he had detected was genuine, but that nature's rhythm was more subtle than he had imagined. He also lacked the confidence or perhaps the audacity to leave gaps in his table where elements might be missing, to suggest that his system revealed not just the organization of known elements, but the existence of unknown ones. The chemistry community's harsh dismissal of Newlands reflected a broader struggle within science during this era. Scientists had become suspicious of grand theoretical schemes after centuries of having to separate genuine natural philosophy from mysticism and speculation. The alchemists had seen patterns everywhere, finding 7s and 3s and magical correspondences that turned out to be illusions. Chemists had worked hard to establish their field as rigorous and empirical, and they were wary of anything that seemed to prioritize pattern over substance. But in their caution, they had missed something important. Newlands had glimpsed the genuine periodicity of the elements. Even if his specific formulation was imperfect, his work represented a crucial stepping stone in understanding the natural world, even though it would take years for this to be recognized. As the 1860s drew to a close, the question of how to organize the elements remained open. Chemists knew more than 60 elements existed. They could measure atomic weights with reasonable precision, and several researchers had noticed that similar elements seemed to cluster together. But no one had yet produced an organizational system that commanded widespread acceptance. The truth was waiting to be discovered, and it would soon emerge from an unexpected place far to the east, from a Russian chemist with a wild beard and an even wilder imagination. As the 1860s drew to a close, the scientific world found itself in a curious state of productive confusion. Chemists had identified more than 60 elements, but these fundamental building blocks of matter seemed to resist any truly satisfying organization. John Newlands had proposed his law of octaves, suggesting that elements repeated their properties every 8th position when arranged by weight, but his idea had been met with skepticism and even mockery. The chemical community remained divided, uncertain whether elements followed any universal pattern at all, or whether they were simply a random collection of substances that nature had scattered throughout the universe, without rhyme or reason. Into this uncertain landscape stepped a Russian chemist whose life had been marked by both hardship and extraordinary determination. Dmitry Ivanovich Mendeleev was born in 1834 in the Siberian town of Tobolsk, the youngest of at least 14 children. His father, a teacher, had gone blind shortly after Dmitry's birth, plunging the large family into financial difficulty. His mother, Maria, took over management of a glass factory to support the family, demonstrating a resilience that her youngest son would inherit. When the glass factory burned down and tragedy continued to strike the family, Maria made the exhausting journey across Russia to St. Petersburg, determined that young Dmitry would receive a proper education. She died shortly after seeing him admitted to the Pedagogical Institute, her mission complete. These early experiences shaped Mendeleev into a man of fierce determination and independence of thought. He possessed a wild, flowing beard that he trimmed only once a year, regardless of social expectations or even imperial commands. Legend holds that when Tsar Alexander II himself asked who the shaggy-looking chemist was, an aide replied that Mendeleev was Russia's greatest chemist, adding that while the Tsar could command many things, Mendeleev's beard answered to no one. This physical appearance matched his intellectual approach. Mendeleev was not a man to trim his ideas to fit conventional expectations. By the late 1860s, Mendeleev was teaching chemistry at the University of St. Petersburg and growing frustrated with the available textbooks. None of them presented the elements in a way that made sense to him, or that would help his students understand the relationships between different substances. He decided to write his own textbook, Principles of Chemistry, and this practical need drove him to wrestle seriously with the question of how to organize the elements. He wrote the name of each known element on a separate card, along with its atomic weight and key properties. Then he began to arrange and rearrange these cards, searching for a pattern that would illuminate the nature of matter itself. The story has been told many times that the answer came to Mendeleev in a dream. After struggling with the arrangement for days, exhausted and frustrated, he fell asleep at his desk and dreamed of a table where all the elements fell into place according to their properties. He awoke and quickly wrote down what he had seen. Later he would say that only one correction was needed to what the dream had revealed. Whether this account is literally true, or whether it represents the kind of myth-making that often surrounds moments of scientific insight, we cannot know with certainty. What matters is that by February 1869, Mendeleev had created an arrangement that would transform chemistry forever. His insight combined simplicity with audacity. He arranged the elements primarily by increasing atomic weight, as others had attempted before him. But Mendeleev did something different. When the properties of an element didn't fit the pattern, he was willing to break the strict order of atomic weights to keep elements with similar properties in the same vertical column. Even more remarkably, when no known element seemed to fit a particular position, he simply left a gap, asserting with supreme confidence that these gaps represented elements not yet discovered. Mendeleev's table, in its 1869 form, would look somewhat foreign to modern eyes. He arranged it with elements in rows according to their atomic weights, but the periodicity he recognized meant that elements sharing similar properties appeared in the same vertical groups. The alkali metals, lithium, sodium, potassium, formed one family. The halogens, fluorine, chlorine, bromine, iodine, formed another. The patterns that Newlands had glimpsed but failed to convince others of now appeared with greater clarity and completeness. The true genius of Mendeleev's approach lay not in the arrangement itself, but in his willingness to trust the pattern over the data. When tellurium and iodine seemed to be in the wrong order based on their atomic weights, Mendeleev boldly placed them according to their properties instead, suggesting that either the atomic weight measurements were incorrect or that some deeper principle was at work. History would prove him right. Atomic number, not atomic weight, is the true organizing principle, though this wouldn't be understood for several more decades. But nothing demonstrated Mendeleev's confidence more dramatically than those empty spaces he left in his table. These weren't merely gaps to be filled someday, if convenient. Mendeleev studied the patterns surrounding these blank spaces and made specific, detailed predictions about the properties of elements that no human had ever seen or isolated. He predicted their atomic weights, their densities, their colors, their melting points, and how they would react with other substances. For three elements in particular, which he called Eka-boron, Eka-aluminum, and Eka-silicon, using the Sanskrit word Eka, meaning one, to indicate they sat one place below known elements, his descriptions were remarkably precise. Mendeleev presented his periodic system to the Russian Chemical Society in March 1869. The response was mixed. Some chemists recognized the power of his organizational scheme. Others remained skeptical. Unlike Newlands, however, Mendeleev had the advantage of making testable predictions. Science respects bold claims that can be verified or refuted through experiment and discovery. The question now was whether nature would cooperate with what this bearded Russian chemist had dreamed. As he refined and defended his table over the following years, Mendeleev became increasingly convinced that he had uncovered something fundamental about the architecture of matter. The periodic table wasn't merely a convenient filing system for chemists. It reflected a deep truth about how the universe constructs the material world. Elements weren't random creations, but members of families, connected by invisible threads that governed their behavior. In finding the pattern, Mendeleev had glimpsed the grammar of existence itself, the rules by which nature writes the story of substance. Now the scientific world would wait and watch. Would these predicted elements emerge from laboratories and ore samples around the world? Would they possess the properties this Russian professor had so confidently described? The answers would come soon enough, and they would astonish everyone. With his periodic table now arranged before him, Mendeleev found himself in possession of something far more powerful than a mere organizational chart. He held what he believed to be a window into the fundamental architecture of nature itself, and if his arrangement truly reflected the underlying order of elements, then it should be able to do something remarkable. predict the future. The gaps in Mendeleev's table weren't mistakes or oversights. They were prophecies waiting to be fulfilled. Where other scientists might have shuffled elements around to eliminate empty spaces, Mendeleev embraced these gaps with the fervor of a man who had glimpsed a deeper truth. These weren't absences, he insisted. They were placeholders for elements that existed somewhere in the earth, waiting to be discovered. Imagine the audacity of this position. Here was a Russian chemist, working far from the prestigious laboratories of Western Europe, declaring that he could describe in detail the properties of substances that no one had ever seen, touched, or isolated. It was the kind of claim that could make or break a scientific reputation. Mendeleev knew this, yet he proceeded anyway. Driven by an unshakable confidence in his arrangement, he focused his attention on three particular gaps, three missing pieces in his grand puzzle. He called them Eka-boron, Eka-aluminum, and Eka-silicon. The prefix Eka came from Sanskrit, meaning one, because each of these predicted elements sat one space below a known element in his table. Eka-aluminum, for instance, would sit one position below aluminum. This naming convention reflected Mendeleev's belief that elements in the same column shared family resemblances, and that these missing elements would combine the properties of their neighbors. For Eka-aluminum, Mendeleev made predictions that were breathtakingly specific. He declared that this undiscovered element would have an atomic weight of about 68. It would be a metal, he said, but not a particularly reactive one. Its density would be approximately 6 grams per cubic centimeter. It would melt at a low temperature for a metal. It would form an oxide with a particular formula, and that oxide would dissolve in both acids and alkalis. He predicted the element would likely be discovered through spectroscopy, as a faint line in a spectrum. He even described how its compounds would behave when crystallized. These weren't vague pronouncements suitable for broad interpretation. They were precise, measurable predictions that could be tested. They were either right or wrong, with little room for ambiguity. Every additional detail Mendeleev provided was another opportunity for his theory to fail. For Eka-boron, Mendeleev predicted an atomic weight near 44, with properties intermediate between calcium and aluminum. For Eka-silicon, he foresaw an element with an atomic weight of 72, a density around 5.5 grams per cubic centimeter, and a dark gray color. He described how each would react with oxygen, what sorts of compounds they would form, and even how those compounds would crystallize. The scientific community's reaction to these predictions ranged from skeptical interest to outright dismissal. Many chemists found Mendeleev's confidence presumptuous. After all, what gave him the right to declare what nature had or hadn't created? The periodic table itself was still controversial, still competing with other organizational schemes. Some scientists saw it as a useful teaching tool, but nothing more. Certainly not a predictive instrument that could peer into the unknown. Mendeleev, however, was not a man easily discouraged. His personality combined the mystical soul of a Russian wanderer with the rigorous mind of a scientist. He had grown up in Siberia, the youngest of at least 14 children, raised by a mother who had fought against tremendous odds to ensure his education. That background had given him both humility and extraordinary determination. He knew what it meant to be dismissed by established authorities, and he knew how to persist. He defended his table tirelessly, writing letters, publishing papers, giving lectures. He engaged with critics, not with dismissive arrogance, but with passionate argument, backed by reams of data. When other chemists pointed out anomalies or questioned his arrangement, Mendeleev would dive back into his calculations, sometimes revising his predictions, sometimes holding firm. He treated his periodic table not as a finished monument, but as a living theory that could grow and adapt while maintaining its essential structure. What made Mendeleev particularly interesting was his willingness to prioritize chemical properties over atomic weights when they conflicted. He had noticed that if he arranged elements strictly by increasing atomic weight, certain elements with obviously similar properties would end up in different columns. So he made the bold choice to occasionally ignore weight order to keep families together. He placed tellurium before iodine, for instance, even though tellurium was slightly heavier, because their chemical behaviors demanded it. Critics pounced on these reversals as evidence that the table was arbitrary. that Mendeleev was simply forcing elements into a pattern he wanted to see, rather than discovering a natural order. But Mendeleev argued that the small discrepancies in atomic weights must be due to measurement errors. He trusted his chemical intuition more than the imperfect measurements of his era, a gamble that seemed either brilliant or foolish depending on one's perspective. As the 1870s progressed, Mendeleev's predictions sat like a challenge to the chemical community. Finding these elements became something of a holy grail for ambitious researchers. Imagine being the chemist who could prove or disprove this grand theory. Imagine discovering a new element and getting to check it against Mendeleev's detailed prophecy. The stakes could hardly have been higher. Mendeleev himself continued his broader work in chemistry, but the periodic table remained his consuming passion. He refined it, defended it, and waited with the patience of a man who had planted seeds and trusted in the harvest. He had done something audacious. He had claimed to read nature's blueprint. Now he needed nature to confirm that he had read it correctly. The empty spaces in his table stared out from the page, 3 gaps among many, 3 specific predictions among his various forecasts. Eka-boron, Eka-aluminum, and Eka-silicon remained stubbornly undiscovered. With each passing year, skeptics grew more confident that these might be phantoms, products of an overactive pattern-seeking imagination, rather than real elements waiting in the earth. But Mendeleev never wavered. He knew what his table was telling him, and he believed that sooner or later, the world would discover he was right. Mendeleev had drawn his map of the chemical world, leaving blank spaces where he insisted undiscovered elements must exist. He had described these missing pieces with remarkable specificity, assigning them properties, weights, and behaviors as if they were old friends he simply hadn't met yet. But maps are only valuable if they lead somewhere real. Predictions mean nothing until they prove true. And so, as the 1870s unfolded, the scientific world watched with a mixture of curiosity and skepticism, waiting to see whether this Russian professor's bold claims would crumble under the weight of reality or stand as monuments to genuine insight. The first vindication came from an unexpected quarter. Paul-Émile Lecoq de Bois-Baudran, a French chemist with a particular talent for spectroscopy, was examining samples of zinc ore in his laboratory in August of 1875. Spectroscopy was still a relatively new technique, involving the heating of substances until they glowed, and then examining the light they emitted through a prism. Each element produced its own unique pattern of colored lines, a kind of optical fingerprint that could reveal its identity. As Lecoq de Bois-Baudran studied the spectrum from his zinc sample, he noticed something peculiar, a violet line that shouldn't have been there, a signature that matched no known element. Working with meticulous care through the remainder of that year, Lecoq de Bois-Baudran managed to isolate a tiny amount of this new substance. It was a soft, silvery metal that melted at an unusually low temperature. He named it gallium, after Gallia, the Latin name for France, though some whispered that the name also played upon his own name, since Lecoq means the rooster, and the Latin word for rooster is gallus. Either way, the element was real, and Lecoq de Bois-Baudran announced his discovery to the French Academy of Sciences with considerable pride. Then came the extraordinary moment that would transform Mendeleev's reputation from that of an interesting theorist to something approaching a prophet. When the properties of gallium were carefully measured, they matched almost exactly what Mendeleev had predicted for his missing element, Eka-aluminum. Mendeleev had said Eka-aluminum should have an atomic weight around 71. Gallium's turned out to be near 70. He had predicted a density of about 6 grams per cubic centimeter. Gallium's was found to be 5.9. He had described how it would be discovered and what its compounds would look like, and reality followed his script with uncanny precision. There was a brief moment of tension when Lecoq de Bois-Baudran's initial measurements gave gallium a density of only 4.7, which seemed to contradict Mendeleev's prediction. But Mendeleev, confident in his system, wrote to the French chemist suggesting that the measurement must be wrong. One can only imagine how Lecoq de Bois-Baudran must have felt receiving this letter from a Russian professor he had never met, telling him his experimental results were incorrect. Yet when he refined his measurements with a purer sample, the density indeed turned out to be higher, falling right in line with Mendeleev's prediction. The periodic table had reached across Europe to correct an experimental error. 4 years later, in 1879, the second confirmation arrived. Lars Fredrik Nielsen, a Swedish chemist working in Uppsala, was investigating the rare earth elements, those confusing substances that seemed to blur together in frustrating similarity. While examining a mineral called ausenite, Nielsen isolated yet another new element. He called it scandium, after Scandinavia, his homeland. At first, this discovery seemed unrelated to Mendeleev's predictions, just another addition to the growing catalogue of elements. But then Per Theodor Clave, another Swedish chemist, examined scandium more carefully and realized something remarkable. This new element's properties matched what Mendeleev had predicted for Iskar boron, the element that should fit in the gap below boron in the periodic table. The atomic weight, the oxide formation, the general chemical behavior, all aligned with Mendeleev's description from a decade earlier. 2 blank spaces on Mendeleev's table had now been filled with real elements, plucked from minerals and matched against predictions as if following a treasure map. The final triumphant confirmation came in 1886. Clemens Winkler, a German chemist at the Freiberg Mining Academy, was analyzing a silver ore called argyrodite, found in a mine near Freiberg. The composition of this mineral was puzzling. When Winkler added up the percentages of all the elements he could identify, they came to only about 93%. Something was missing, some substantial component that kept eluding identification. After painstaking work, Winkler managed to isolate this mystery substance, a grayish-white element with properties unlike anything in the known catalogue. As Winkler characterized this new element, he felt the mounting excitement of recognition. Its atomic weight was around 72. It formed an oxide with specific properties. Its density, its appearance, its chemical reactions, everything about it resonated with a description he had read in the scientific literature. This was aca-silicon, the third of Mendeleev's predicted elements. Winkler named it germanium, after his homeland, and his announcement sent ripples through the international chemistry community. The accuracy of the match was breathtaking. Mendeleev had predicted an atomic weight of 72. Germanium's was 72.6. He had predicted a density of 5.5. Germanium's was 5.3. He had described the properties of its oxide, its chloride, and its general behavior, and germanium performed as if it had read Mendeleev's script and memorized its lines. Even the method of its discovery, hidden as a minor component in a mineral ore, followed the pattern Mendeleev had suggested. With these 3 discoveries, gallium, scandium, and germanium, the periodic table underwent a transformation in the eyes of the scientific world. What had seemed like an interesting organizational scheme, perhaps a bit too clever and too speculative, now revealed itself as something far more profound. The table wasn't just arranging known elements, it was revealing deep structural truths about matter itself. The patterns Mendeleev had perceived were real patterns, not imposed by human imagination, but discovered in the fabric of nature. Letters of congratulation flooded in from scientific societies across Europe. Mendeleev, who had fought so hard to defend his table against critics and skeptics, now found himself celebrated as one of the great scientific minds of the age. The periodic table became required knowledge for chemistry students, no longer a curiosity, but a fundamental tool. And perhaps most satisfying of all, those who had ridiculed or dismissed Mendeleev's predictions now had to acknowledge that this eccentric Russian professor had seen further into the nature of matter than anyone before him. As the scientific community settled into sleep on those nights in the late 1880s, they could rest with a new confidence. The elements weren't just a random collection of substances, they formed a system, a family with relationships and patterns that could be understood and predicted. 3 empty chairs at Mendeleev's table had been filled, and those who sat down in them had arrived exactly as invited, wearing precisely the characteristics described on their place cards. The universe, it seemed, was more knowable than they had dared to hope. With the triumphant confirmation of Mendeleev's predictions still echoing through laboratories across Europe, chemists might have hoped that the periodic table would now fall into neat, orderly rows, but nature, as it so often does, had other plans. hidden among the elements already discovered, lurked a particularly troublesome family that would challenge scientists for decades. These were the rare earth elements, a collection of metals so remarkably similar to one another that separating them was like trying to sort identical twins in a darkened room. The story of this confusion begins in 1787 in a small quarry near the village of Uteby in Sweden. This unremarkable mining site would become perhaps the most honored location in chemical history, eventually lending its name to 4 different elements. An amateur mineralogist named Carl Axel Arrhenius discovered an unusual black rock there, a heavy mineral unlike anything previously documented. He called it Utebite, after the village, and sent samples to chemists across Scandinavia, unknowingly setting off a puzzle that would occupy some of the finest minds in chemistry. The Finnish chemist Johann Gaudelin examined this strange mineral and managed to extract from it a new earth, an oxide that didn't match any known element. This discovery, announced in 1794, was eventually named yttria in honor of the quarry. Scientists initially believed they had found a single new element, but yttria held secrets that would take nearly a century to fully unravel. Locked within that one mineral were not one, but several different elements, each maddeningly similar to the others. Enter Carl Gustaf Mosander, a Swedish chemist working in the early decades of the 19th century. Mosander possessed extraordinary patience and an almost supernatural ability to detect subtle differences in chemical behavior. In the 1840s, he began methodically examining yttria and another rare earth compound called ceria, which had been isolated from a different mineral. Through countless experiments involving fractional crystallization, a technique where substances are dissolved and recrystallized repeatedly to separate components that behave only slightly differently, Mosander teased apart what others had assumed were single elements. From ceria, Mosander separated lanthanum in 1839, revealing that what chemists had called cerium was actually a mixture. Then he turned his attention back to yttria, that mysterious substance from Uteby. Through painstaking work, he demonstrated that yttria contained not one element, but at least 3. He named them yttrium, terbium, and erbium, though even these would later prove to be mixtures themselves. The rare earth puzzle was deepening rather than resolving. What made these elements so confoundingly similar? We now know they belong to a group called the lanthanides, elements with atomic numbers from 57 to 71. These elements share an unusual property. As you move across this series, additional electrons are being added not to the outermost shell, but to an inner shell buried deep within the atom. This means that the outer electron configuration, which determines most chemical behavior, remains nearly identical across all these elements. They form compounds with the same formulas, display similar colors, and react in almost indistinguishable ways. For 19th century chemists without sophisticated analytical tools, separating them was an extraordinary challenge. The work required almost superhuman dedication. A chemist might perform hundreds or even thousands of crystallizations to obtain a reasonably pure sample, and even then, uncertainty lingered. Was this truly a pure element, or did it contain traces of yet another undiscovered lanthanide? The spectroscope, which analyzed the wavelengths of light emitted by heated elements, provided some help. Each element produces a unique pattern of spectral lines, like a fingerprint of light, but even this tool could be deceiving when dealing with mixtures of such similar substances. As more chemists examined rare earth minerals through the late 19th century, the list of suspected elements grew confusing. Names were proposed, then retracted. Elements were announced, only to be revealed as mixtures of other elements. The French chemist Paul-Émile Lecoq de Bois-Baudran, who had discovered gallium and confirmed one of Mendeleev's predictions, also worked extensively with rare earths. He isolated new elements including samarium, named after the mineral samarskite, and dysprosium, from the Greek word meaning hard to get at, a perfectly appropriate name given the difficulty of isolating it. The Austrian chemist Karl Auer von Welsbach made significant contributions by separating praseodymium and neodymium from what had been called didymium, which means twin in Greek. The name was fitting, as these two elements were so alike that earlier chemists had assumed they were one. Welsbach later separated ytterbium and lutetium from other rare earths, further untangling the web of similar elements. For Mendeleev, the rare earth elements presented a unique organizational challenge. Where did they belong in his periodic table? They couldn't each occupy separate positions, as that would destroy the patterns that gave the table its predictive power. Yet they were clearly distinct elements, not different forms of the same substance. The solution, though Mendeleev himself didn't fully resolve it, was eventually to place them in a separate series, acknowledging that they formed a special family within the table's structure. Today we display them in a separate row at the bottom of the periodic table, along with the actinides, another series with similar properties. The rare earth puzzle also revealed something profound about the nature of the periodic table. The table wasn't merely a grid of boxes to be filled, it had depth and structure reflecting the complex architecture of atoms themselves. The lanthanides showed that periodicity involved layers of repetition, with some properties repeating regularly, while others followed more subtle patterns. These elements were nature's reminder that simplicity in science often conceals deeper complexity. By the early 20th century, chemists had finally mapped out all the naturally occurring lanthanides. The rare earth puzzle had been largely solved. Though working with these elements remained challenging, they found important applications nonetheless. Cerium became crucial for lighter flints and polishing compounds. Neodymium would eventually become essential for powerful permanent magnets. These once obscure substances from a Swedish quarry had secured their place, not just in the periodic table, but in technology itself. As the 19th century drew to a close, chemists could look back on decades of detective work that had revealed this hidden family of elements. But even as the rare earth puzzle neared its solution, another surprise awaited. An entirely new group of elements was about to be discovered. Elements so unreactive that they had remained invisible, despite being present in the air everyone breathed. The periodic table was about to gain an unexpected new column. The confusion surrounding the rare earth elements had tested the patience and skill of chemists for decades, but at least those elements fit somewhere into the emerging understanding of the periodic system. What happened in the 1890s was something altogether different and unexpected. An entirely new family of elements appeared, elements that Mendeleev had never predicted, elements that seemed to refuse to participate in chemistry at all. The story begins with a puzzle about weight. In the late 1880s, Lord Rayleigh, a meticulous British physicist with a reputation for precision measurements, noticed something curious about nitrogen. When he prepared nitrogen by removing oxygen and other known gases from air, it was slightly denser than nitrogen prepared by chemical means from ammonia compounds. The difference was tiny, less than 0.5%, but Lord Rayleigh was the sort of scientist who trusted his instruments and believed that nature never made mistakes. If there was a discrepancy, there had to be a reason. For several years, this puzzle bothered him. He published a note in Nature magazine in 1892, essentially asking if anyone could explain this mysterious difference in density. Most scientists ignored the question, dismissing such a small variation as experimental error, but one chemist took the puzzle seriously. William Ramsay, a Scottish chemist working at University College London, had a curious mind and loved solving mysteries. He wrote to Lord Rayleigh, suggesting they work together on the problem. Their collaboration led to a remarkable discovery. By painstakingly removing every known component from air, oxygen, nitrogen, carbon dioxide, water vapor, they found that a small fraction remained, something that wouldn't react with anything they tried. This stubborn residue was heavier than nitrogen, which explained Lord Rayleigh's original observation. In 1894, they announced the discovery of a new element, which they named argon, from the Greek word meaning lazy or inactive, because it refused to form compounds with any other element. The announcement created immediate controversy. Where did argon fit in the periodic table? It had an atomic weight that would place it between chlorine and potassium, but there was no gap there in Mendeleev's arrangement. Moreover, argon didn't behave like either of its supposed neighbors. Chlorine was viciously reactive. Potassium burst into flame when exposed to water, yet argon did absolutely nothing. It seemed to exist in splendid isolation. indifferent to all the other elements around it. Mendeleev himself was skeptical. He had not predicted any such element, and the discovery threatened the beautiful order of his table. Some scientists suggested argon might not be an element at all, but perhaps a compound of nitrogen, or maybe an unusual form of known elements. But Ramsay and Rayleigh's evidence was solid. Argon was real, and chemistry would have to accommodate it. Ramsay suspected that if one such element existed, there might be others. He began searching with characteristic enthusiasm. He had heard of experiments by the American chemist William Hillebrand, who had noticed that certain uranium minerals gave off an inert gas when heated. Most chemists assumed this was nitrogen, but Ramsay obtained samples of these minerals and tested the gas carefully. In 1895, he discovered it was not nitrogen at all, but another unreactive element. Spectroscopic analysis revealed lines that matched those of helium, an element previously known only from the sun's spectrum, observed during solar eclipses. Ramsay had found helium on Earth. Now there were two of these strange, unreactive elements. Ramsay became convinced that an entire family awaited discovery. He reasoned that if argon and helium existed, there should be others with intermediate atomic weights. He and his assistant Maurice Travers began a systematic search. They acquired large quantities of argon and subjected them to fractional distillation at extremely low temperatures, carefully separating components that boiled at different temperatures. In the summer of 1898, their patience was rewarded. In June, they isolated a new gas that produced a brilliant orange-red glow when electricity passed through it. They named it krypton, from the Greek word for hidden. Just a few weeks later, they found another, even rarer gas and called it neon, meaning new. Finally, in September, they discovered the rarest of all, which they named xenon, meaning stranger. In just 4 years, an entire column of elements had been added to the periodic table. Ramsay called them the noble gases, suggesting they held themselves aloof from common elements, like nobility refusing to mingle with commoners. The name captured their essential character perfect. These elements had complete outer electron shells, though that would not be understood for another decade. Their self-contained electronic structure meant they had no need or tendency to gain, lose, or share electrons with other elements. The challenge was determining where this new family belonged in the table's structure. Eventually, it became clear they should occupy an entirely new column, now known as Group 18, placed at the far right side of the table. This required a conceptual shift in how chemists thought about the periodic table. It was not a finished structure that simply needed gaps filled in. It was a dynamic framework that could expand to accommodate new discoveries while maintaining its essential logic. The discovery of the noble gases represented a triumph of careful observation and systematic investigation. Lord Rayleigh's refusal to dismiss a tiny discrepancy in measurements had opened the door to an entirely unsuspected realm of chemistry. Ramsay's systematic search had filled out the family. Together they had shown that nature still held surprises, even for the most comprehensive scientific theories. For his discoveries, Ramsay received the Nobel Prize in Chemistry in 1904, while Lord Rayleigh had already received the Nobel Prize in Physics in 1904 for the discovery of argon. The noble gases also provided important clues about atomic structure that would become clear in the following decades. Their complete lack of reactivity pointed toward something fundamental about electron arrangement and chemical bonding. As the 19th century drew to a close, the periodic table had weathered its first major test from unexpected discoveries. The noble gases had been accommodated without destroying the table's basic structure. The framework Mendeleev created had proven flexible enough to expand, robust enough to incorporate the genuinely surprising, and the stage was now set for even more dramatic discoveries that would reveal elements that could transform into other elements entirely. As the 19th century drew to a close, chemists had grown comfortable with their periodic table. The noble gases had found their place, the patterns seemed secure, and the fundamental elements appeared stable and unchanging. Then, in the final years of the 1800s, nature revealed one of its most profound secrets, one that would shake the very foundations of what scientists believed about matter itself. The story begins quietly in Paris, where a physicist named Henri Becquerel was investigating phosphorescence, the gentle glow that certain materials emit after being exposed to light. In February of 1896, Becquerel was working with uranium salts, planning to expose them to sunlight before testing whether they would fog photographic plates wrapped in dark paper. But the Parisian weather refused to cooperate. Cloudy skies persisted, and Becquerel tucked his experimental materials into a drawer, placing the wrapped photographic plates alongside uranium-containing crystals while he waited for sunshine to return. Days passed. Finally, perhaps simply curious or perhaps impatient, Becquerel developed the plates that had sat in darkness with the uranium. To his astonishment, the plates were fogged as thoroughly as if they had been exposed to bright light. The uranium was emitting some kind of invisible rays, not from stored sunlight, but from within the material itself. This spontaneous emission of energy seemed to violate everything chemists understood about the stability of elements. Becquerel published his findings, but the discovery initially attracted little attention. Then a young Polish scientist named Maria Skłodowska, who had recently married French physicist Pierre Curie, decided to investigate these mysterious rays for her doctoral research. She began her work in a converted shed, equipped with basic instruments and an intense determination to understand what uranium was doing. Marie Curie, as she became known, methodically tested every element and compound she could obtain. Measuring the strength of the rays they emitted, she discovered that thorium also produced these rays, and she coined a new term for this phenomenon: radioactivity. But the most startling finding came when she measured pitchblende, the ore from which uranium was extracted. The pitchblende was far more radioactive than pure uranium itself. This made no sense unless the ore contained other, even more radioactive elements that no one had yet isolated. Working in their primitive laboratory through the Parisian winter, with no proper heating and barely adequate ventilation, Marie and Pierre Curie began the exhausting work of chemically separating the components of pitchblende. Ton after ton of the ore arrived, and the Curies dissolved, precipitated, crystallized, and separated its components in an industrial-scale chemical process that seemed more like factory work than scientific research. Marie stood over bubbling cauldrons, stirring massive vats with iron rods nearly as tall as herself, breathing in vapors that would later prove harmful. In July of 1898, the Curies announced their first discovery. They had isolated a new element that was 400 times more radioactive than uranium. Marie chose to name it polonium, after her native Poland, which at that time was partitioned and absent from maps of Europe. The element was intensely radioactive but present in such tiny quantities that extracting even a measurable sample required processing enormous amounts of ore. They didn't stop there. By December of the same year, the Curies announced a second discovery, an element even more remarkable than polonium. They named it radium, from the Latin word for ray. Radium glowed with its own light, a pale blue-green luminescence visible in the darkness of their shed. This ethereal glow seemed almost magical, a visible manifestation of the invisible energy streaming from within the atom. Proving that radium was truly a new element required years of additional work. Marie Curie needed to isolate enough pure radium to determine its atomic weight precisely, and to study its spectral lines, the unique fingerprints that confirmed an element's identity. This meant processing even more pitchblende, performing the same tedious separations over and over. By 1902, Marie had finally purified 1/10 of a gram of radium chloride from several tons of ore, enough to measure its properties definitively. The discovery of radioactivity fundamentally challenged what it meant to be an element. Since the time of Lavoisier, elements had been defined as substances that could not be broken down into simpler substances through chemical means. They were thought to be eternal and unchanging. But radioactive elements were spontaneously transforming, shooting out pieces of themselves and becoming different elements in the process. Radium, it turned out, slowly transformed into radon gas, which itself transformed into other elements in a chain of decay. Ernest Rutherford, working across the English Channel, was unraveling what was happening inside these radioactive atoms. He discovered that radioactive decay came in different types, which he named alpha and beta rays. Alpha particles were revealed to be helium nuclei. massive projectiles ejected from the centers of radioactive atoms. Beta particles were high-speed electrons. Each emission transformed the parent atom into a different element. The alchemists' dream of transmutation was real after all, but it happened spontaneously in nature rather than through mystical processes in laboratory vessels. This understanding created a new challenge for the periodic table. Radioactive decay produced chains of elements, some of which had never been seen before. Many of these elements were unstable, existing only briefly before transforming again. Scientists began discovering isotopes, atoms of the same element with different weights because they contained different numbers of neutrons. Some isotopes were stable, while others were radioactive. The work took a toll on those who pursued it. Marie Curie carried test tubes of radium in her pockets and stored them in her desk drawer, fascinated by their glow in the dark. The Curie's notebooks from this period are still radioactive today, stored in lead-lined boxes and viewable only with special precautions. Pierre Curie died in 1906 in a street accident, but Marie continued the work, becoming the first woman to win a Nobel Prize and the only person to win Nobel Prizes in two different sciences, physics and chemistry. The understanding of radioactivity opened entirely new sections of the periodic table. Beyond uranium, element 92 lay a realm of elements that existed only fleetingly in nature or had to be created artificially. The table was no longer simply a catalogue of stable substances found in the Earth, but a map that extended into territories of instability and transformation. The elements, it turned out, had hidden depths that earlier chemists could never have imagined, and the periodic table would need to expand and adapt to encompass these radioactive discoveries and all that would follow from them. As the 19th century gave way to the 20th, the periodic table had become an established fixture of scientific thought. Mendeleev's arrangement had proven its worth through successful predictions, and the discovery of the noble gases had expanded it in unexpected ways. Yet despite its practical success, nobody truly understood why the table worked. The patterns were undeniable, but the underlying cause of these patterns remained shrouded in mystery. The elements repeated their properties in regular intervals. Families of elements shared similar behaviors, but the reason behind this periodicity was as elusive as morning mist. The answer would come from an unlikely direction, not from studying the elements themselves, but from peering inside the atom into a realm so small that it defied the imagination of even the most visionary scientists. In 1897, while working at the Cavendish Laboratory in Cambridge, a physicist named J.J. Thomson made a discovery that would forever change our understanding of matter. Through his experiments with cathode ray tubes, those glass vessels filled with low-pressure gas and fitted with electrodes, Thomson identified something smaller than an atom. He called these tiny particles corpuscles, though we know them today as electrons. The atom, long considered the smallest, indivisible unit of matter, was itself made of something smaller. It was like discovering that grains of sand were themselves made of even tinier particles. Thomson imagined atoms as something like plum puddings, with negatively charged electrons embedded throughout a sphere of positive charge, like raisins in a traditional English dessert. It was a comforting model, suggesting that atoms were soft, uniform things without hard edges or empty spaces. But this gentle vision would not survive long. Ernest Rutherford, a New Zealander with a booming voice and an outsized personality, conducted an experiment in 1909 that shattered Thomson's plum pudding model. Working with his assistants Hans Geiger and Ernest Marsden at the University of Manchester, Rutherford directed a beam of alpha particles at an extremely thin sheet of gold foil. If Thomson's model were correct, these particles should have passed through the soft uniform atoms with barely any deflection, like bullets through fog. Most of the alpha particles did indeed pass straight through, but some bounced back at sharp angles, and a few even rebounded directly backward toward the source. Rutherford later recalled his astonishment, saying it was as if you had fired an artillery shell at tissue paper and it had bounced back and hit you. The only explanation was that atoms were mostly empty space, with nearly all their mass concentrated in an incredibly tiny, dense nucleus at the center. The electrons, Those minuscule charged particles must orbit this nucleus at relatively vast distances, like planets around a distant sun. This nuclear model of the atom was revolutionary, but it created new puzzles. What determined which element an atom belonged to? Why did elements show periodic properties? The answers began to emerge from unexpected corners of the scientific world. In 1913, a young English physicist named Henry Moseley made a discovery that would tragically prove to be his most lasting contribution to science. Working at the University of Oxford, Moseley was studying the X-rays emitted by different elements when they were bombarded with electrons. He noticed a clear mathematical relationship between the frequency of these X-rays and the position of each element in the periodic table. Moving from one element to the next increased the X-ray frequency in a regular, predictable pattern. Moseley realized that this pattern reflected something fundamental about atomic structure. Each element's nucleus contained a specific number of positive charges, which he called the atomic number. Hydrogen had 1, helium had 2, lithium had 3, and so on up the table. This atomic number, not the atomic weight that Mendeleev had used, was the true organizing principle of the periodic table. This revelation solved several nagging problems that had troubled chemists for decades. Mendeleev had occasionally been forced to place heavier elements before lighter ones to maintain chemical similarities. Tellurium, for instance, was heavier than iodine, but had to come before it in the table. Moseley's work showed that tellurium's atomic number was indeed lower than iodine's, validating Mendeleev's instinct to prioritize chemical properties over atomic weight. Moseley's atomic numbers also revealed precisely how many elements remained to be discovered. The gaps in the sequence showed exactly where unknown elements must eventually be found. It transformed the search for new elements from a matter of chemical exploration into a systematic filling of numbered slots. Tragically, Henry Moseley's brilliant career was cut short in 1915 when he was killed by a sniper's bullet at Gallipoli during the First World War. He was just 27 years old. Many scientists believed he would have certainly won a Nobel Prize had he lived. His death prompted some in the scientific community to argue that scientists of exceptional talent should be protected from military service, though such arguments came too late for Moseley himself. The discoveries of electrons, the nuclear atom, and atomic numbers finally provided a physical foundation for the periodic table's patterns. Elements were defined not by their weight or their chemical properties, but by the number of protons in their nucleus. This number determined how many electrons orbited that nucleus, and those electrons, as scientists were beginning to understand, were responsible for all of chemistry. The picture was becoming clearer, though many details remained fuzzy. Each element had a specific number of electrons surrounding its nucleus, and somehow the arrangement of those electrons determined whether an element was a reactive metal, an unreactive noble gas, or something in between. The electrons held the secret to periodicity, to the repeating patterns that Mendeleev had recognized but could not explain. As the 1910s progressed, physicists around the world worked to understand how electrons were arranged around the nucleus and why certain arrangements led to similar chemical properties. The answer would require diving even deeper into the quantum realm, into a world where particles behaved like waves and certainty gave way to probability. But those discoveries belonged to the next phase of the story, when the full explanation of the periodic table's architecture would finally emerge from the revolutionary new physics of the quantum age. The atom's interior, once thought to be impenetrably small and forever hidden from human understanding, had begun to reveal its secrets. By the early decades of the 20th century, scientists had made tremendous progress in understanding what lay beneath the surface of matter. They knew that atoms contained a dense nucleus at the center, surrounded by negatively charged electrons. They understood that the number of protons in the nucleus determined an element's identity and its position in the periodic table. Yet one profound mystery remained unsolved. Why did elements arranged by atomic number display such beautifully repeating patterns of chemical behavior? Why did lithium, sodium, and potassium all behave similarly? Why did fluorine, chlorine, and bromine share such striking characteristics? The answer, it turned out, lay in the invisible architecture of electrons surrounding each atomic nucleus. The story of understanding electron arrangement is filled with brilliant minds working at the frontiers of physics and chemistry, often collaborating across borders despite the turmoil of World War I and its aftermath. Danish physicist Niels Bohr emerged as a central figure in this unfolding drama. Working in Ernest Rutherford's laboratory in Manchester, England, in 1913, Bohr proposed a revolutionary model of the atom that would transform our understanding of the periodic table's structure. Bohr suggested that electrons didn't simply swarm randomly around the nucleus like bees around a hive. Instead, they occupied specific orbits or shells at fixed distances from the nucleus, much like planets orbiting the Sun at different distances. Each shell could hold only a certain maximum number of electrons, and electrons filled these shells in a particular order, starting with the shell closest to the nucleus. This was a radical departure from earlier thinking, and it introduced a new kind of quantum thinking into atomic structure. The innermost shell, Bohr calculated, could hold only 2 electrons. The second shell could accommodate up to 8 electrons. The pattern continued outward, with each successive shell having its own maximum capacity. Most importantly for understanding chemistry, Bohr recognized that an atom's chemical properties depended primarily on the number of electrons in its outermost shell, which came to be called the valence shell. This insight illuminated the periodic table like a lantern in the darkness. Hydrogen, with atomic number 1, had just a single electron in its first shell. Helium, with atomic number 2, had 2 electrons, completely filling that innermost shell. A filled shell, Bohr realized, created extraordinary stability, which explained helium's remarkable reluctance to form chemical bonds. It was perfectly content with its complete electron shell. Moving to lithium, with atomic number 3, the pattern revealed its elegance. With 3 electrons total, lithium's first shell was filled with 2 electrons, and the third electron had to begin a new second shell. This single electron in the outermost shell made lithium highly reactive, always eager to give away that lonely outer electron to achieve the stability of a filled shell. As we move across the second period of the table, each element added 1 more electron to that second shell. Beryllium had 2 electrons in its outer shell. Boron had 3, carbon had 4, and so on. When we reached neon, with atomic number 10, the second shell became completely filled with 8 electrons. Like helium before it, neon achieved the stability of a complete outer shell, making it another noble gas with almost no chemical reactivity. The pattern repeated with striking regularity. Sodium, the next element, had to start a third shell with a single outer electron, making it behave almost identically to lithium. Both had 1 electron in their outermost shell, explaining why they occupied the same column in the periodic table. The beauty of this electron shell model was its explanatory power. Elements in the same column of the periodic table, the model showed, had the same number of electrons in their outermost shell. All the alkali metals in the first column had 1 outer electron. All the halogens in the second to last column had 7 electrons in their outer shell, making them desperately eager to grab 1 more electron to complete their shell. The noble gases in the final column all had complete outer shells, explaining their splendid isolation from chemical reactions. Building on Bohr's foundation, other scientists refined the model further. The American chemist Gilbert Lewis, working at the University of California, Berkeley, developed the concept of the electron pair bond in 1916. Lewis showed how atoms could achieve stable electron configurations, not just by giving away or accepting electrons, but by sharing them with other atoms. His simple diagrams, showing electrons as dots around element symbols, became an indispensable tool for chemists trying to understand how molecules formed. As quantum mechanics developed through the 1920s, physicists including Wolfgang Pauli, Werner Heisenberg, and Erwin Schrödinger further refined our understanding of electron behavior. Pauli introduced his exclusion principle in 1925, explaining why each orbital within a shell could hold only 2 electrons with opposite spins. Schrödinger's wave equation treated electrons not as tiny particles in defined orbits, but as clouds of probability existing in regions called orbitals with characteristic shapes and energies. These quantum mechanical refinements revealed that the simple picture of shells was actually more complex. Each shell contained subshells with different shapes, designated by letters S, P, D, and F. The S subshell was spherical and could hold 2 electrons. The P subshells had dumbbell shapes and could collectively hold 6 electrons. The D subshells, with more complex geometries, accommodated 10 electrons, while the F subshells could hold 14. This subshell structure explained features of the periodic table that had previously seemed arbitrary. The table's characteristic shape, with its varying column widths, reflected the filling of different subshells. The first 2 columns represented the filling of subshells. The 6 columns on the right side of the main table corresponded to P subshells filling. The 10-column-wide transition metals in the middle represented D subshell filling, while the lanthanides and actinides, usually shown as separate rows below the main table, represented the filling of F subshells. The electron configuration of each element became its unique address in the quantum world. Iron, for instance, could be described as having the configuration that filled shells and subshells in a specific pattern, with its characteristic properties arising from the particular arrangement of its outer electrons. This electronic fingerprint determined everything about how iron behaved chemically, what compounds it formed, what colors those compounds displayed, how it conducted electricity, and its magnetic properties. Perhaps most remarkably, the electron shell model transformed the periodic table from a mysterious arrangement that happened to work into a profound expression of quantum mechanical principles. The table's periods corresponded to the filling of electron shells. The groups or columns reflected elements with similar outer electron configurations. Every gap Mendeleev had left, every pattern he had intuited, every periodicity he had recognized, all flowed naturally from the quantum rules governing electron arrangement. As we settle into the comfort of this understanding, we can appreciate how the periodic table became not merely a catalogue of elements, but a map of electronic possibility. Each element occupies its unique position because of the precise number of electrons it possesses and the quantum rules that dictate how those electrons must arrange themselves. The table's familiar form, with all its characteristic shapes and sections, is nothing less than the visible expression of invisible quantum laws, a bridge between the abstract mathematics of electron orbitals and the tangible world of chemical reactions and material properties. The understanding of electron shells and atomic structure had finally explained why the periodic table looked the way it did, but this knowledge opened an intriguing new question. If scientists understood the fundamental principles governing the elements, could they perhaps create new ones? Could human ingenuity extend nature's work and add entirely new entries to Mendeleev's table? For most of history, such thoughts would have seemed like pure fantasy, the modern equivalent of the Alchemists' impossible dreams. But by the 1930s, the technology and understanding had advanced to a point where creating new elements became not just possible, but inevitable. The key lay in understanding that an element's identity was determined solely by the number of protons in its nucleus. Change that number, and you transformed one element into another. The first synthetic element came into being almost by accident. In the mid-1930s, scientists in Italy and Germany were bombarding various elements with neutrons and other particles, studying what happened when atomic nuclei absorbed these projectiles. Element 43, sitting in that gap Mendeleev had left in his table, remained stubbornly undiscovered in nature. Some scientists had claimed to find it, but their findings never held up to scrutiny. The reason, though nobody knew it yet, was that element 43 simply doesn't exist naturally on Earth in any meaningful quantity. Every atom of it that ever formed had long since decayed away. In 1937, a sample of molybdenum foil that had been bombarded with particles in a cyclotron in Berkeley, California, made its way to Italy. Emilio Segre and Carlo Perrier carefully analyzed this irradiated sample and found something remarkable. The bombardment had transformed some of the molybdenum atoms into element 43. They named it technium, from the Greek word teknetos, meaning artificial. For the first time in human history, an element had been deliberately created rather than discovered. This achievement opened floodgates of possibility. If one element could be synthesized, why not others? The focus soon shifted to the elements beyond uranium, element 92. Uranium was the heaviest element found in nature, in appreciable quantities, sitting at what seemed to be the edge of the periodic table, but perhaps that edge could be pushed further. A brilliant and ambitious chemist named Glenn Seaborg entered this story in the early 1940s. Working at the University of California, Berkeley, Seaborg and his colleagues began systematically creating elements heavier than uranium. In 1940, they produced neptunium, element 93, by bombarding uranium with neutrons in a cyclotron. The name followed astronomical logic. Just as the planet Neptune lies beyond Uranus, neptunium would sit beyond uranium on the table. Just months later, in early 1941, Seaborg's team created element 94. They named it plutonium, continuing the astronomical theme, since Pluto was considered the next planet beyond Neptune at the time. What none of them could fully anticipate was how plutonium would change the world. This synthetic element proved to have extraordinary properties related to nuclear fission, and within a few years, plutonium would become central to the Manhattan Project. But in those early months, it was simply another fascinating addition to the growing list of synthetic elements. Seaborg possessed not just scientific brilliance, but also remarkable organizational vision. As his team continued creating new elements through the 1940s and 1950s, americium, curium, berkelium, californium, einsteinium, fermium, mendeleevium, nobelium, and lawrencium, he recognized a pattern. These transuranium elements didn't quite fit where conventional table arrangements suggested they should go. They behaved more like the lanthanides, that confusing series of rare earth elements that sat separately at the bottom of the table. In a bold move that echoed Mendeleev's confident reorganization decades earlier, Seaborg proposed that elements 89 through 103 formed a second series similar to the lanthanides, which he called the actinide series. This meant these elements should also be placed in their own row at the bottom of the table. The chemistry establishment initially resisted this reorganization, but as evidence accumulated, Seaborg's actinide concept became accepted. He had not only created new elements, but had also restructured the periodic table itself to accommodate them. The creation of synthetic elements required increasingly sophisticated equipment and techniques. Early efforts used cyclotrons, machines that accelerated particles to high speeds and smashed them into target materials. Later, scientists employed nuclear reactors, using the intense neutron flux inside reactors to transform elements. Some elements were even isolated from the debris of nuclear weapons tests, their atoms forged in the extreme conditions of nuclear explosions. As scientists pushed further into the transuranium elements, each new creation became progressively more difficult. The target elements became rarer, the required energies higher, and the resulting atoms more unstable. Some of these synthetic elements existed for only fractions of a second before decaying into lighter elements. Scientists had to identify them from just a handful of atoms, sometimes even single atoms, using increasingly clever detection methods. Glenn Seaborg's contributions to element synthesis were so significant that when element 106 was created in 1974, scientists eventually named it Seaborgium in his honor. Remarkably, Seaborg was still alive when this happened, making him the first person to have an element named after them, while they could still appreciate the honor. He reportedly quipped that this made him one of the few people who could say they were in their element, quite literally. By the latter decades of the 20th century, creating new elements had become an international endeavor, with laboratories in Russia, Germany, Japan, and the United States all competing and collaborating. Each new element required years of painstaking work, massive particle accelerators, and teams of dedicated scientists. The synthetic elements had moved far beyond anything with practical applications. These were explorations into the fundamental limits of matter itself. The techniques for creating super-heavy elements grew increasingly sophisticated. Scientists learned to aim beams of one element's ions at targets of another element, hoping that occasionally nuclei would merge to create a new, heavier element. Success rates were astonishingly low. Creating a single atom of a super-heavy element might require weeks of continuous bombardment, with billions upon billions of collisions, yielding perhaps one successful fusion. Yet, despite the difficulties, the work continued. Each new synthetic element represented a victory of human curiosity and ingenuity, pushing the boundaries of the periodic table into realms that nature, at least on Earth, had never explored. These elements existed only because humans had learned enough about atomic structure to deliberately craft them, atom by painstaking atom, extending Mendeleev's table far beyond anything its creator could have imagined. As the 20th century drew to a close, the periodic table had grown to include dozens of elements that existed only because scientists had willed them into being, each one a testament to how far human understanding had progressed since those ancient Greek philosophers first wondered what everything was made of. As scientists succeeded in creating element after element beyond uranium, pushing the periodic table into territories nature had never explored, a curious pattern began to emerge. The super-heavy elements they were crafting existed for mere fractions of a second before decaying into lighter elements. Element 104, Rutherfordium, might last a few seconds at best. Element 105, Dubinium, flickered in and out of existence even more quickly. Each step up the ladder of atomic numbers seemed to produce elements that were increasingly unstable, vanishing almost as soon as they appeared. This presented scientists with both a practical challenge and a theoretical puzzle. The practical challenge was obvious. How could you study an element that existed for microseconds? How could you confirm its properties, measure its characteristics, or even prove beyond doubt that you had created it? The theoretical puzzle was equally intriguing. If elements kept becoming more and more unstable as they grew heavier, would there come a point where elements simply couldn't exist at all? Was there a natural limit to the periodic table, a point beyond which no element could survive even for an instant? But in the 1960s and 1970s, theoretical physicists began proposing something remarkable. Their calculations suggested that while the general trend toward instability would continue, there might be certain combinations of protons and neutrons that created particularly stable configurations. These special numbers, dubbed magic numbers, occurred when nuclear shells were completely filled, much like how filled electron shells created the stable noble gases. The theory predicted that if you could create an element with just the right number of protons and neutrons, it might exist for dramatically longer periods than its neighbors on the periodic table. These hypothetical long-lived super-heavy elements would sit on what theorists called an island of stability, surrounded by a sea of extremely unstable elements. The most promising candidate seemed to be an element with 114 protons and 184 neutrons, though other islands might exist at even higher atomic numbers, perhaps around element 120 or 126. These islands wouldn't contain stable elements in the traditional sense, but their inhabitants might survive for minutes, days, or even years, rather than microseconds. The quest to reach this island became one of the great challenges of nuclear physics. Laboratories around the world began competing to create the super-heavy elements that might prove the theory right. The Joint Institute for Nuclear Research in Dubna, Russia, the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany, the Riken Laboratory in Japan, and the Lawrence Berkeley National Laboratory and Lawrence Livermore National Laboratory in the United States all joined the race. Creating these super-heavy elements required extraordinary patience and enormous particle accelerators. Scientists would take atoms of a lighter element and accelerate them to tremendous speeds, then smash them into targets made of other heavy elements, hoping that occasionally two nuclei would fuse together to create something heavier than either parent. The probability of success was infinitesimally small. You might need to fire trillions upon trillions of projectile atoms at your target before a single atom of your desired element appeared. The Russian team in Dubna had particular success in this realm. Working with American scientists from Livermore, they created element 114, flerovium, in 1998. The atoms they produced lived for several seconds, noticeably longer than simple theories would have predicted. This suggested they might indeed be approaching the shores of the island of stability. They pushed onward, creating element 115 moscovium, and eventually element 118 oganesson, in 2002. Element 118 holds a special place in the periodic table. Sitting at the bottom of the noble gas column, directly below helium, neon, argon, krypton, xenon, and radon, it represents the completion of the 7th row of the periodic table. Creating even a few atoms required a feat of extraordinary persistence. The scientists bombarded Californium targets with calcium ions for months, conducting an experiment that involved something like 10 quintillion particle collisions. From this almost incomprehensible number of attempts, they detected just 3 atoms of element 118, each surviving for less than a millisecond before decaying. The German laboratory at Darmstadt, meanwhile, focused on different approaches and different target elements. Their meticulous methods and independent confirmations helped verify many of the discoveries made by other laboratories. This cross-verification became increasingly important as the elements grew more exotic and short-lived. When you're claiming to have created something that exists for microseconds and produces only a handful of atoms, other scientists need to be able to reproduce your results. The process of confirming these super-heavy elements became a complex detective story. Scientists couldn't simply bottle up a sample and examine it at leisure. Instead, they had to identify elements by their decay signatures, the characteristic ways they broke apart into lighter elements. Each super-heavy element followed a unique decay chain, like a fingerprint, as it shed particles and transformed through a series of lighter elements before finally reaching something stable. By carefully measuring the energies and timings of these decay events, scientists could work backwards to determine what they had created. The naming of these super-heavy elements became a matter of international diplomacy. Element 114 was named fluorovium, after Georgy Flyarov, the founder of the Dubna laboratory. Element 115 became moscovium, honoring the Moscow region. Element 116 received the name livermorium, recognizing the American laboratory's contributions. Element 117, tennessine, honored Tennessee's Oak Ridge National Laboratory and its contributions to element research. And element 118, the heaviest element currently confirmed, was named Oganesson, after Yuri Oganessian, the Russian physicist who led many of the super-heavy element discoveries. As scientists pushed beyond element 118, the experimental challenges multiplied. The production rates dropped even lower. The decay times became even shorter. But the theoretical predictions of the island of stability kept researchers motivated. Somewhere ahead, perhaps at element 120, perhaps at element 126, there might exist atoms that defy the trend, that remain intact long enough to truly study their chemistry, to understand their properties, to see if they behave as the periodic table predicts. These experiments continue today, with laboratories planning attempts to create elements 119 and 120. The facilities required are enormous. The experiments take months or years, and success is never guaranteed, yet the pursuit continues, driven by humanity's fundamental curiosity about the nature of matter. Each new element, no matter how briefly it exists, represents a triumph of human ingenuity and persistence, another step in a journey that began when ancient philosophers first wondered what the world was made of. The journey of discovery that began with ancient philosophers pondering earth, water, air, and fire has brought us to a remarkably complete picture. As we settle into our final moments together, let us contemplate the periodic table as it exists today, a magnificent tapestry of 118 confirmed elements, each with its own story, each occupying its precise place in this elegant arrangement. On November 30th, 2016, the International Union of Pure and Applied Chemistry officially recognized the names of the final 4 elements needed to complete the 7th row of the periodic table. Nihonium, moscovium, tennessine, and oganesson took their places, filling in the last empty squares and bringing a sense of completion to this corner of the table. The names themselves tell stories of collaboration and achievement. Nihonium honors Japan, where it was synthesized at the Riken Laboratory. Moscovium acknowledges Moscow and the Joint Institute for Nuclear Research in Dubna. Tennessine celebrates Tennessee and Oak Ridge National Laboratory's contributions to heavy element research, and Oganesson pays tribute to Yuri Oganesson, the Russian physicist whose career spanned decades of super-heavy element creation. The naming of these elements sparked discussions and gentle controversies, as such decisions often do. Scientists debated pronunciations and the appropriateness of honoring living scientists, a practice once avoided but now accepted. These conversations reminded everyone that the periodic table remains a living document, shaped not just by nature's laws, but by human decisions and international cooperation. Today's periodic table arranges its 118 elements in 7 horizontal rows, called periods, and 18 vertical columns called groups. The arrangement might seem arbitrary at first glance, with that curious detachment of the lanthanides and actinides at the bottom, but every aspect reflects deep truths about atomic structure. The number of an element's row tells you how many electron shells surround its nucleus. The column reveals how many electrons occupy that outermost shell, which determines nearly everything about how that element behaves chemically. The table's shape itself tells a story. The 2 tall columns on the left contain the highly reactive metals like sodium and potassium. The 6 tall columns on the right house everything from reactive non-metals like oxygen to the serene noble gases. The broad middle section holds the transition metals, a diverse family including iron, copper, gold, and all those other elements that form colorful compounds and make excellent conductors. The 2 rows tucked underneath the main table, the lanthanides and actinides, represent elements whose chemistry is so similar within each series that they almost refuse to be organized at all. Every chemistry classroom, every laboratory, every textbook displays some version of this table. It has become such a familiar sight that we might forget how revolutionary it remains. No other scientific tool compresses so much information into such an elegant format. Glance at any element's position, and you immediately know its approximate atomic mass, its likely chemical behavior, whether it forms positive or negative ions, how many bonds it typically creates, and how it compares to its neighbors. The table continues to serve as a guide for practical applications. Materials scientists use it to predict which combinations of elements might create useful alloys or semiconductors. Pharmaceutical researchers consult it when designing new medicines, knowing that elements in the same group often play similar biological roles. Environmental scientists track elements through ecosystems by understanding their chemical similarities and differences. The table has become indispensable precisely because it works, because nature truly does organize matter according to these patterns. As we gaze at the complete 7th row, questions naturally arise about what comes next. Could there be an 8th row? A period 8 stretching out with room for new discoveries? Theoretically, yes. The mathematics of quantum mechanics suggests that period 8, if it could exist, would hold 50 elements, from element 119 through element 168. Some of these predicted elements occupy scientists' imaginations. Element 120, the first member of this hypothetical new row, would be an alkaline earth metal sitting directly below radium. Element 146 might be a noble gas, completing a new column. But theory and reality diverge dramatically at these extreme atomic numbers. The challenges that made creating Oganesson so difficult would intensify enormously. These super heavy elements would exist for vanishingly brief moments if they could be created at all. The technical requirements for smashing together the necessary atomic nuclei become almost unimaginable. Perhaps future technologies will make such syntheses possible. Or perhaps we have reached the practical limits of the periodic table's expansion. The beauty of the periodic table lies not in its completion, but in what it represents: humanity's patient effort to understand the fundamental building blocks of everything around us. From the oxygen we breathe to the calcium in our bones, from the silicon in computer chips to the tungsten in light bulb filaments, every element tells part of the story of our universe. The table organizes not just elements, but the very fabric of material existence. Scientists continue discovering new things about elements we have known for centuries. Researchers explore how elements behave under extreme pressures or temperatures, revealing properties that textbooks never mentioned. They investigate how elements combine in unexpected ways, or discover new roles elements play in biological systems. The periodic table provides the framework for all these investigations, a constant reference point in an ever-expanding field of knowledge. In laboratories around the world tonight, researchers continue working with these elements. Some attempt to create fleeting glimpses of element 119 or 120. Others probe the properties of more familiar elements, seeking applications or understanding. The same table that guides a student through basic chemistry homework also guides cutting-edge research into quantum computing, renewable energy, and countless other frontiers. As our story draws to a close and your breathing deepens, picture the periodic table one last time. See it not as a static chart, but as a living map of discovery, marked with the footsteps of centuries of curious minds. From ancient Greek philosophers to medieval alchemists, from Lavoisier's careful measurements to Mendeleev's bold predictions, from the Curie's glowing radium to modern particle accelerators, creating elements that exist for less than a second, the journey has been remarkable. The periodic table stands complete for now, yet somehow unfinished. It invites new questions, suggests new experiments, and promises discoveries yet to come. It remains one of humanity's greatest intellectual achievements, a testament to our desire to understand, to organize, to find patterns in nature's complexity. And there it rests, ordered and elegant, waiting for tomorrow's discoveries. As we bring to a close our journey through the remarkable story of the periodic table, from ancient alchemists to modern scientists, we hope these tales of discovery, and the curious minds behind them, have gently carried you through the evening. Thank you for joining us on this peaceful exploration of how we came to understand the very building blocks of our world. If these calm adventures have brought you comfort, we'd love to have you with us again. Please like, subscribe, and share your thoughts in the comments below to help other smart sleepers find their way here. And now, as the night deepens and your mind settles, we wish you the sweetest of dreams. Good night, fellow dreamer, and may your sleep be restful and your dreams be kind.